Now let's take a look at the pyro solver settings to create an explosion. Okay, so here onto the pyro solver, let's go on to the bounds and onto the boundary condition. Let's click treat y as close below, so it means that below 0 our container boundaries will act as a collider. Okay, so now here as you can see we are colliding with our floor. Okay, and right now our flames and smoke are dissipating quickly, so let's go on to the fields tab, and in here let's lower the dissipation, so let's make it a very low value to 0.01. okay, so now we are adding very little dissipation for our smoke. Okay, and let's go on to the sourcing, and in here let's increase the divergence to add more expansion, so let's increase this to 5 and hit play. Okay, and let's go back onto the shape tab, and in here let's enable the flame expansion, and here we are using the flame field to add the expansion. So into the flame range let's adjust this to 0.1. okay, and let's hit play. And right now as you can see our simulation is not rising high enough, and that is because the temperature. Okay, so the temperature will affect the buoyancy. So here onto the shape tab we have the buoyancy, so the buoyancy is the force that is causing the smoke to rise up. Okay, and it is directly related to the temperature. Okay, so here onto the operation is set to pull. Let's add the temperature into our scene. Okay, and now let's hit play, and here as you can see just by changing the temperature to add, now our simulation is rising fast. Okay, so let's decrease the temperature scale to 0.2. okay, and also let's decrease our velocity volume to a lower value. Let's change this to 0.2 as well and hit play. Okay, so now our simulation is starting to look more like an explosion. Okay, and after that let's go on to the shape tab and let's lower our buoyancy. Right now our simulation is rising fast. Okay, so let's lower the buoyancy scale, set this to 0.5 and hit play. Okay, the buoyancy scale of 0.5 is looking good, and here as you can see at the pyro solver we are using the flame field for our fire. Okay, so for the rendering we are going to use the temperature field. Okay, so this look tab is not displaying the correct volume, so let's add a pyro bake volume node. Okay, so we are going to use this node to render our explosion, and onto the pyro bake volume let's enable the scatter. Okay, and here onto the scatter, if you go onto the bindings and collapse the scatter, here as you can see we are using the temperature for our fire. Okay, so we are going to use the temperature volume for our fire, and here you can adjust the intensity, we can adjust this parameter later when we are rendering. Okay, so let's hit play. And here is our explosion. Let's break up our simulation by adding some velocity noise. Okay, so let's go into the pyro solver and onto the shape tab. Let's enable the disturbance and also the turbulence. Let's here add a very small value of turbulence. Let's change this to 0.75 and hit play. Right now we have a very coarse simulation. Okay, so we will see more detail when we lower our voxel size. Okay, so let's go back onto the shape and let's increase the disturbance and set this to 50 to add a higher disturbance. And let's also enable the control field and use the speed field to add the disturbance. Okay, so let's go into the field and enable the speed field for our calculation. Okay, so we want to disturb our simulation only where our explosion is moving. Okay, so when our explosion is rising, we want to disturb that. So when the smoke has come to rest, I don't want it to be disturbed. Okay, and onto the speed field, let's use the range 1 to 5. Okay, and if you want to check your current speed field range, so you can visualize your speed field by going onto the field and onto the field guide. Let's enable our speed guide visualization and hit play. And to view the speed field, we need to set the display flag onto the pyro solver node. Okay, so here as you can see, we have the speed field visualized. So if I collapse that folder, we have the setting. So by default it will be set to 3D. Okay, so we are visualizing the speed volume in 3D space. So let's change this to plane. Okay, so now we are slicing our volume to visualize our speed field. And here we have the guide range. So right now for our disturbance we are using the range 1 to 5. Okay, so let's view this 1 to 5. Okay, so these are the areas that we are applying the disturbance. Okay, and here you can adjust the parameter to better visualize. Okay, so let's change this to no guide, and when we change our simulation to high res, we will see more details. Okay, so let's set the display flag to the pyro bake volume node, and let's dive inside the pyro solver node. And in here let's add gas vortex confinement, and onto the vortex confinement let's increase the confinement scale to 5. Okay, so this will boost our noise velocities. Okay, and let's see. And here as you can see, we are adding a lot more detail to our explosion. So let's select a good camera angle for our explosion, and let's set our frame range to 120. And onto the pyro solver let's lower our voxel size to 0.2, and let's check with the high res simulation. Okay, so here as you can see, we are adding a lot more detail. Okay, let's go back onto the fields tab, and here let's enable the density emission from flame. Okay, and here we have the option for the temperature cooling rate. Okay, so right now the cooling rate is set to 0.5, so let's lower the cooling rate to 0.2. so now our explosion will rise more. Okay, because we have a low cooling rate of our temperature. So here onto the pyro solver, let's change this back to 0.6 again, and let's see with the cooling rate 0.2. Let's zoom out. And here, as you can see, just by changing the cooling rate, we have a completely different looking explosion. Okay, so let's change this to 0.3. Okay, I think our explosion is looking good. So at the pyro solver, let's go on to the output, and let's disable the flame field since we're not going to use this field for rendering, and let's disable the velocity and the CD. So we are going to write only the density and the temperature. Okay, because these are the two fields that we are going to use for rendering. And let's also convert this to VDB and use the 16-bit float. And this time we're not gonna check this option because we do have density. Okay, so we don't need to check this option, flame density. Okay, and after that let's add a file cache node. And onto the pyro solver, for the final resolution, let's change the voxel size to 0.1. Okay, and let's write out our caches to disk. Okay, all done. So I have written out all the caches, and here onto the pyro solver, I have changed the voxel size to 0.15. The 0.1 was taking too long to simulate. Okay, and if we go on to the first frames, here as you can see we have some clipping problem. So at the pyro solver and the bounds, I forgot to add the padding because our explosion is rising fast. So we have the clipping. So in here add the to 0.6 maybe. Okay, so this will solve the clipping problem. Okay, and now let's generate the smoke trails for our explosion. Okay, so in here let's add a pyro trail node. Okay, so the pyro trail has two nodes. So first one is the trail path. So this node is generating the path. Okay, and let's hit play, and here as you can see we have the animation as well as these guides. Okay, and this one pyro trail source node is generating these actual trails. Okay, so here we are generating these points. Okay, so into the pyro trail path node, here we have the initial size to set the overall size. Okay, and the shape we can change this to line. Okay, let's change this to sphere, and here we have the direction and the number of trailings if you want to add more or less trails. Okay, and here we have the angle as well as the spreading, and we can enable prune by noise to randomly remove some trails. Okay, so now we are removing trails based on the noise. Here we have the element size for noise, and also the roughness and the offset. Okay, let's disable that, and let's decrease the number of trailings, and let's see with our explosion. Okay, so here as you can see our explosion much higher res, so it takes time to load the frame. So let's add a VDB resample node to resample our voxel size. So let's connect that, and here onto the VDB resample, the define transform, let's change this to use the voxel size, and now we can set the voxel size for our volume. Okay, and here as you can see now we are creating a much low res volume. Okay, this is for the viewport performance. Okay, we will remove this node when we are rendering. Okay, so now let's template our trail path. Okay, so here as you can see the trail path, we have very small scale of trailing. So let's go back and let's increase the initial size to 20, and also onto the trail generation we have the velocity scale. So let's increase the velocity scale, and here we can adjust the particles drag as well as we can add mass. Okay, so let's view the animation, and onto the pyro trail we have the duration. So if you want to create your trail for longer duration, you can increase that. So let's increase this to 100, and now as you can see our trails now will live for 100 frames. Okay, so let's change this back to 72, and let's enable the length noise. Okay, so now some of our trail have longer length and some are shorter. Okay, and onto the pyro trail source node. So this node is generating these points. So here we have the trailing shape. We can adjust the particle separation to add more particles, and also the length. So let's increase the length a bit, and here we can create more thick or thin trails. Okay, so the particle separation is looking good, and let's also enable the trailing noise. Let's increase the amplitude, and here we have the element size for our noise. Okay, and let's go into the trail animation. We have the option to offset the animation, also the speed scale for increasing the speed. Let's go into the trail component. So let's add a temperature as well. So let's create the source and change this to temperature, and also check the prefix attribute. So this will add a prefix trail. So if I middle click here, as you can see we have the density and we have the prefix trail, and then we have the name temperature. Okay, and let's also enable scale along trailing to add the scale, and also scale over duration for fading. Okay, and here onto the quick setup. let's create the pyro simulation. Okay, and onto the voxel size, let's increase this to 0.5 and hit play. Okay, let's go into the field and let's lower the density dissipation to 0.05 to add less dissipation in our trails. And also let's go into the look tab and increase the density scale. Let's change this to 50. And let's also go into the sourcing. So we are using the density and the operation is maximum. Let's change this to add. Okay, and let's also go back onto the trail source node and let's increase the overall thickness of our trailing. So let's increase the radius. Okay, and let's also increase the length. Now let's check our simulation. Okay, now let's view this with our explosion. So let's add an merge. Let's merge both of these volumes. Okay, so here we have the trailings. So let's offset our trailings. So right now trailings are generated at the first frame. Okay, so let's go into the pyro trail path node and here onto the start frame, let's change this to frame 10. Okay, so now we are generating this trail on the 10 frame. Okay, and let's also go on to the pyro trail source node and let's increase the particle separation to 0.07. Okay, so the 0.07 value is looking good. Here onto the volume rasterize attribute, so we are using the voxel size of 0.07. So let's delete this channel and let's use the same voxel size as our pyro solver. So let's copy this parameter and paste relative reference. Okay, now let's go back and adjust the radius. Let's change this to 0.3 and hit play. Okay, let's go into the pyro solver and onto the fields. Let's disable the temperature emission and also disable the flame. We don't need that. And let's lower the density dissipation to even low, 0.01. Okay, I think the trailings are looking good. Okay, in here as you can see we are creating an volume density and the trail temperature. Okay, so let's split this volume. So in here let's add a blast node and onto the blast let's select the add name trail temperature and click the delete non-selected. Okay, so now we are isolating the trail temperature, and after that let's go into the pyro solver and onto the output let's uncheck the temperature, flame, velocity and the CD and choose convert to VDB, use 16-bit float, and let's merge both of these volume density and the trail temperature. Okay, and after that let's add an pyro bake volume node to create the shader. Let's connect it here and let's increase the density scale to 50 and also go into the secondary fire and let's enable that. And if you go into the bindings and into the secondary fire. Here as you can see, we are using the trail temperature volume for secondary fire. Okay, so here we can adjust the intensity of our trails. Okay, so here we have our trailings. So onto the pyro solver, let's decrease the voxel size to 0.2 maybe. Okay, the voxel size of 0.2 is looking good. So let's add a file cache node and cache out our trailing. Okay, so here are the smoke trail cache, and here as you can see, we are keep adding more smoke into our simulation. Okay, so here onto the pyro solver, I increase the dissipation to 0.05, and also onto the sourcing, I change the operation back to maximum. Okay, and if I go into the file cache and take a look at the version 2, and here is the result of changing these settings. Okay, so these trails looks more natural. Okay, so these are the settings I am using for the final smoke trails. Okay, now let's create the blast rings for our explosion. So in here, let's add a pyro first source, and onto the pyro first source, onto the first type, let's change this to blast ring, and let's go back, and here we have the blast rings. So let's increase the initial size, set the display flag to our explosion, and let's template our pyro burst source. Okay, so let's add the blast ring at the frame number 30. So here onto the pyro burst source, go into the burst animation, and here onto the start frame, let's set this to 30. Okay, so now we are generating the blast ring on frame 30, and let's also increase the frame duration and also increase the overall expansion. Okay, and let's go back onto the burst shape. Let's increase the distribution length, and let's also change the distribution along height, and now we can adjust this ramp. So let's select the first point of our ramp, and let's zero it out, and onto the second point, let's zero it out as well, and also increase the distribution length. Let's decrease the rings per blast to 3, add the 3 rings, and let's also increase the initial size. Let's change this to 15. Okay, so now we have the big rings, and let's also decrease the point separation to generate more points. And here we have the trailing depth, so let's lower the trailing depth, and let's decrease the initial size. Okay, and let's check, and let's adjust the height, and let's bring this point down to lift up our rings, and let's also increase the ring depth, and let's also add the shape noise, and let's set the display flag to the rings, and here let's adjust the amplitude, and here is the size of our noise. Okay, So let's go into the burst animation, and let's also increase the frame duration. Let's change this to 48 frame, and let's see. So let's go back and let's adjust this ramp position. Okay, let's go into the burst animation and let's increase the frame duration. Let's change this to 60, and so the frame duration of 60 is looking good. And go into the quick setup. Let's create a source volume. Okay, and let's increase the voxel size to 0.1, and let's check. Okay, so we are adding the velocity and the burn and the temperature into our volume rasterize attribute. So let's go into the pyro burst source and onto the output attribute. Let's disable the velocity, and onto the burst component let's remove the temperature, we don't need that, and also the burn field, we don't need that. Okay, so now we are only creating a density volume. Okay, let's increase the particle scale to fill out this sparse volume. Okay, let's change this to 2, or maybe let's change this to 1.5. Okay, so the value of 1.5 is looking good. So let's merge this into our scene and let's check. Okay, so our blast rings are starting as a solid volume. So let's go into the pyro burst source and enable the scale over duration, and let's adjust the duration ramp to create the fading. Okay, so now we have the fading animation. Okay, let's enable the scale along trailing to fade out the outer layer of our blast rings. Okay, so these are our blast rings. In here let's add a pyro bake volume node to create the shader for our blast ring. So let's connect that, and in here we have the density scale. Okay, so let's keep that at 1 for now, and let's add a null, and let's call this one blast rings. Okay, and let's also add null here as well. Let's connect that, and let's call this one trails, and let's also add a null here, and let's call this one out explosion. Okay, and let's delete this merge node, we don't need that. Okay, so now in the next lesson let's render our explosion. Okay, now let's render our explosion. So first let's see how we can render this using Mantra, and then we will import this into Solaris and render this in Karma. Okay, so let's go back. In here let's create another geometry container for our smoke trails as well as for the blast rings. Okay, so in here let's add another geometry node, and let's call this one trails, and let's add another geometry node, and let's call this one blast rings, and let's dive inside the trail geometry node, and in here let's add an object merge. Okay, we will use the object merge node to import the smoke trails from our main sim. So let's call this one main sim. Okay, so in here onto the object merge, let's select the object from our main sim, import our trails null. Okay, and let's go inside the blast ring, and in here let's add another object merge node and select the blast rings null. Okay, so let's go forward. Okay, so here we have these blast rings. Now let's add a light, and onto the light let's change the type from point to distant light. Distant light is like a sunlight. Okay, so for this light the translation doesn't matter. Okay, so only the rotation will change the lighting direction. Okay, so let's rotate this, and here as you can see we have the guide for the lighting direction, and let's rotate this in X. Okay, and also let's add a light from this direction. Bring up the shelf, press and hold the control key and click on this area light. So now the light is created from the current viewing angle. Okay, so now we are looking through the light. Here as you can see we have the area light selected and the lock button is on, so which means I can select my camera tool and position the light. Okay, so let's add the light from this direction. Let's unlock it. Okay, and now let's select an angle for rendering. So maybe this angle, and press and hold the control key and click on the camera to create a camera from the view, and let's select the camera tool, lock is on, and position the camera. Okay, let's unlock it, hide the shelf. Okay, so here onto the camera, onto the view tab, you can define your final render resolution. Okay, so now let's go on to the out, and in here let's add a lantern node, and let's go into the render view and select our cam1, and before rendering let's go on to the object, and let's into the main sim, let's remove our VDB resample node. Okay, so let's click on this bypass button to bypass this node. Okay, so now we are using the full resolution of our simulation. Okay, so now let's go into the render view and press render. Okay, so now the smoke color is looking a bit too white, so let's change the parameter from this shader. So here we have the explosion, and this is the shader for our explosion. So let's go into the smoke tab, and let's change the smoke color to a darkish gray. Okay, so that is too dark, so let's change this to 0.5. Okay, so the 0.5 is looking good. So now let's set the same color for our smoke trails. So here we have the trail, and this is the shader for the trail. So let's go into the smoke and change the smoke color to 0.5. And also for the shock wave, here we have the shader for the blast waves. So in here, let's change its color to 0.5. So these are the values that you can keep changing to your liking. Okay. So let's stop this. And let's go back. Let's go into the out section and here onto the mantra. Select the valid frame range. So right now it's set to render current frame. So let's change this to render frame range to render out our whole sequence. And here onto the output picture, select the location that where you want to store the sequences and press render to disk option to render your sequences. Okay. Now let's see how we can render this in Karma. Okay. So for that, let's go into the stage context, and in here let's add a SOP import node, and from here let's import our out explosion from our main sim, and let's call this one explosion. Let's duplicate this SOP import node, and from here let's import our trails, and let's call this one trails, and let's duplicate this again, and let's import our blast rings. Okay, and now let's merge all of them, adding an merge node, and after that let's add a Karma ROP, and let's change the render from here perspective to Karma. Okay, so now we need to set up the materials for our simulation. Okay, so let's change this back to Houdini GL, and in here let's add a material library and connect that, and let's dive inside, and in here let's add a pyro shader. Okay, and let's call this one explosion. Let's duplicate this shader again, and let's create this one for our trails, and let's duplicate this again, and this one for our blast rings. Okay, here onto the explosion, let's change our smoke color to 0.5, half gray, and onto the scatter, let's enable the scatter, and for the trail let's set the 0.5 value for the smoke color, and for the blast ring as well. Let's go back, and in here click on this autofill material to fill these slots, and check assign to geometry, and for the explosion let's select our SOP import explosion, place it here, and let's remove this stage, we don't need that, and let's drag this for the trails, remove the stage, and this one we forgot to remove, we forgot to rename blast rings. Let's drag it here. Okay, and now let's change this to Karma, and in here let's add a light, choose the distant light. Okay, and let's merge this into our scene. Let's go into the transform and rotate this in Y and as well as in X, or let's go back onto the object level, and let's copy the parameter from our this light. So let's copy this and go into the stage and paste it here. Okay, and now let's add an area light for filling all of these dark areas. Okay, control click on the area light to add a light from the current viewing angle, and let's unlock this light, and let me hide the shelf, and the light is down here, so let's bring it up and connect it here. Set the display flag onto the Karma, and in here let's choose the Karma renderer for rendering. Okay, so let's change this to Houdini GL, and let's dive inside the material library. And for our trails, we forgot to enable our scantrifier, so let's enable that. And here onto the bindings, onto the scantrifier, and let's check our volume name. So the volume name is set to trail temperature, so which is correct. Okay, so now let's go back and render this again. Okay, so now we do have trails. Now let's change the background to dark, so let's click on this I button and go into the background and change the color scheme to dark. And onto the area light, let's increase the intensity, and for the distance light, let's go into the basic properties and increase the exposure. Okay, and let's dive inside and adjust our smoke color. So the smoke color is looking more dark, so let's change the value. Okay, so the value of 1 is looking good in the Karma renderer. Okay, so let's change this for our trails as well. Okay, so let me stop the renderer and let's create a camera. So let's click that, select the angle, press and hold the control key and click on the camera icon to create the camera, and let's position the camera, and let me hide the shelf, and the camera is down here, so let's disconnect it from there and let's merge it at the up level and set the display flag onto the Karma. Okay, onto the Karma node, here you can select the resolution and the output picture, select the location, and onto the UST render op, here you can select the valid frame range. So let's change this to render specific frame range, so the range is set to 120, and press render to disk option to render out your sequences. Okay, so here I have rendered out the explosion, and here as you can see we have these trailing, so they are disappearing at the same time, and the blast rings, so these rings are disappearing too quickly. Okay, so to fix that, here onto the object level, here onto the main sim, onto the trail path, I change the timing for our trailing. So here I change the trail duration to 80 and add a variation. So here it was set to uniform, so let's change this to set varying to add a variation. Okay, so now here as you can see some of my trails die quickly. Okay, so here I have randomly set the life of my trailings, and also onto the source I have changed the initial size to 10. Okay, and also for the blast rings, and onto the burst shape I changed the trailing depth to 0.7. Okay, and onto the burst animation I also increased the frame duration to 120. Okay, and here onto the burst component I changed the ramp for a faster initial impact. Okay, so these are the settings that are subject to change Okay, so you can keep adjusting these settings to your liking. And after making these changes, here I have another render. So if I go into the sequence and select this one, okay, so here is the another render. So here now we have these blast rings that last longer. Okay, and also I have rendered only just the explosion without these secondary elements. Okay, so that's the simple explosion render only. Okay, now let's talk about particles, and let's create the particle simulation from scratch. So let's add a geometry node and dive inside, and in here let's add a DOP network. Okay, and dive inside the DOP net. So now we are in the dynamics, and in here to set up the particle simulation we need a pop solver. Okay, so here we have the pop solver. So let's connect this into the out node, and the pop solver need the pop object. Okay, so let's add a pop object node. So the pop object node will contain our particles and all of the attributes. Okay, and now we need a source for the particles emission. Okay, so let's add a pop location node. Okay, and let's connect that. So this last input is for the sourcing. Okay, let's bring up the play bar and hit play, and here we have the very basic particle simulation. Okay, so let's enable the real-time playback, and here onto the pop location we have the option for the emission source position. Okay, here you can adjust the initial position, the X and Y and Z. Okay, and here we have the impulse activation, and impulse activation is set to 1, which means on. So this value is between 0 and 1. So if you want to activate the impulse activation, change this to 1, and if you want to disable the impulse activation, set this to 0. Okay, and here we have the impulse count. So how many particles that you want to emit per frame, and here we have the constant activation. So it is set to 1, which means the constant activation is on. So this value is also in 0 and 1. Okay, so 0 means the activation is disabled, 1 means the activation is on. And here we have the constant birth rate. So this is the particle birth rate, is that how many particles will be emitted during the course of 1 second. Okay, and if you click on this global animation option, here we have the option, and at first we have the FPS. So right now our project FPS is set to 24. So which means at the course of 24 frame we will have that many particles in the sim. Okay, so let's zero it out and set the impulse activation to 1, and let's add the impulse count to 100. And now if you middle click on the pop object, here as you can see we have 100 points, and on to the second frame we will have 200 particles. Okay, and here as you can see on the second frame we have 200 points. So this is the birth rate of per frame, and the constant activation is the birth rate per second. Okay, so let's zero out the impulse activation, and let's enable the constant activation. And down here we have the life expectancy of the particles. So it is set to 100 seconds. So let's change this to 0.5. So this life expectancy is in seconds, and also you can add the variance to the particles. Okay, so here if I play, As you can see, we have particles dying, all of these particles dying at the same time. We can add the variation, so let's enable the life variance. And here, as you can see, some of the particles will have shorter life and some of them will have a longer life. Okay, and we have the jitter burst time. Okay, to explain this, let's remove the pop location, and now let's import our source from geometry to meet the particles. Okay, so let's go back, and in here let's create a source. So let's add a circle, and let's connect that into the pop net, and let's dive inside. And to emit particles from our geometry source, we have a node called pop source. Okay, pop source node, so let's connect that. And here onto the pop source we have the emission type. So the emission type is set to the scatter onto surface. So if I hit play, so nothing happened. That is because the geometry source is set to use parameter value, which means you can define the solve path in here. Okay, or you can change this to the first context geometry. Okay, which means the first input of our .NET. And here, as you can see, we have the guides. Okay, up here we have the guides enabled. You can disable that. Okay, and here, as you can see, we have particles are being born at the surface of our geometry. So because the emission type is set to scatter onto surface, or we can change this to all points. So now it will emit particles from the points of our geometry. Okay, so if I go back, and here let's add a scatter node, and let's connect that. So now here we have the points as an input. So now if we dive inside the .NET, so now we are using the all points of our geometry. Okay, so right now our particles are not moving because currently we don't have any forces. Okay, so let's add a force. So right click, if you type a pop, so all of these nodes with the pop, you can use these nodes with the particle solver. Okay, so all of the nodes with the pop are relevant to the particle simulation. Okay, and in here let's add a pop force node, and let's connect that. And here onto the pop force we have the value. You can set the force in the X, Y, or Z, or we can just enable the noise. Here we have the noise, so let's increase the amplitude to add noise, and let's hit play. And now our particles are moving due to the pop force node. Okay, and you can also create the velocities here at the SOP level, and the particle solver will inherit these velocities as well. So after the scatter node, let's add a point velocity, and let's connect that. And here onto the point velocity, let's set this to value, and let's give him a positive Z value. Let's change this to 1, and let's go back onto the particle solver and hit play. And here, as you can see, now our particles are moving due to the initial velocity, and the pop force is adding the noise. So if I disable that, here, as you can see, the particles are moving due to their initial velocity. Okay, and here onto the pop source, the emission type, we set this to all point, and we here have the option to use the all geometry. So the all geometry means that, so if I disable the scatter and the point velocity, so now we have the circle as a geometry. Okay, so now let's enable the pop force to add the movement to our particles. And here, as you can see, all of our circle geometry has been imported into DOPS. Okay, So let's disable the noise and let's add the force in the positive z direction. Okay, so now here as you can see we are emitting the whole circle geometry. Okay, so that's the all geometry. You can change these 2 points, so now it will emit from the points of our circle. So in here if I add a sphere, let's connect the sphere, and here as you can see now it will use these sphere geometry points for the emission. Okay, and now we are using our sphere geometry points to emit particles. Okay, and you can change this to scatter onto surface. Now it will scatter the particles onto the surface of the sphere. Okay, and next we have the birth tab, and here we have the option for the impulse activation and the impulse count and the constant birth rate and the activation. Okay, and also we have the max particle limit. Okay, so that's the how many particles will be born per frame. So we have this limit, and you can also set the max sim point limit. So now this limit means that many particle will only allowed to simulate. Okay, so if I increase the constant birth rate, okay, so now here as you can see we are not emitting any more particles than this limit. Okay, so if you want to emit more particles you need to disable the max sim point as well as the max points per frame limit. Okay, and here we have the life expectancy and the variance and the jitter burst time. So if I go back and let's connect the circle and hit play, here as you can see we have these particle stepping. Okay, so if we enable the jitter burst timing, so let's change this to negative. So now we don't have the particles stepping anymore because we are jittering the burst timing of these particles. Okay, and next we have the attributes tab. So this will inherit all of the point attributes. Okay, so the star wildcard means that all of the attributes that the particles have will be inherited here into the DOPs. Okay, and here we have the option to the inherit velocity. We can use the inherited velocity, or we can add this velocity to the inherited velocity. Okay, or we can set the initial velocity on our own. So it means that our velocities from the SOP level will be ignored. Okay, so if we use the point velocity node, so now this velocity will be ignored because here we are using our own initial velocity. Okay, and next we have the stream, and the stream name is set to the $OS, which means the operator stream, the operator name itself. So the operator name is set to pop source. So if we middle click, and here as you can see now particles are not generated. So if we go into the source, our geometry source is set to the scatter onto surface emission type, but here we are using the points as a source. Okay, so that is why particles are not being emitted inside the DOP net. So let's change this to all points. Okay, so now we do have points in our particle simulation, and here if you middle click, here as you can see we have the number of particles, and we have some particle attributes, and also we have a point group. So the point group is a stream, it's the pop source 1. Okay, so because the name is set to pop source 1, and here onto the stream we are using the $OS variable, which means the operator name. So if I change this to surface, and now if I middle click, here as you can see we have the point group and the stream is the surface. Okay, so these stream are basically the groups inside of the DOBs. So let's say if we have a multiple source, so let's say here we are emitting particles from this circle, and let's emit also from the sphere as well. So let's go back here onto the .NET and let's add another pop source node, and let's merge both of these sources. Okay, and here onto the pop source, let's use the inside our object in the Geo1, use the sphere. Okay, and the mode is set to scatter onto surface. So now we have two different sources. Let's increase the number of particles. Okay, so now we have these two different streams. So if I add a pop color and connect it here, and let's give him a red color, and let's add another pop color and connect it onto this pop source node. Let's give him a green color. Okay, so here as you can see now we have these two different streams. Okay, and you can also connect these color node down here as well. So if I disconnect that, let's disconnect this pop color node here, and here onto the pop color node, here we have the option to set the groups. So let's enable that, and here onto the groups, here as you can see we have two different streams. So the first stream is the pop source 1 and the stream surface. Okay, so let's change this one to the stream pop source 1, and onto the red let's enable the group, and in here let's use our stream surface. Okay, and now here as you can see we are setting the different color for our different pop sources. Okay, so that's what these streams are. So these are basically the groups. Okay, and if you go back here onto the geometry level, here we have the pop net. So if you type pop, here we have the pop network. Okay, and if you dive inside the pop net, here we have the basic particle simulation setup. Okay, so let's connect that, and here onto the pop source, emission tab is set to scatter onto surface. Let's choose this to all points because we have the points as an input. Okay, and here we have our particle simulation. Now let's talk about particle forces. So let's create a geometry node and dive inside, and in here let's add a circle as an emitter, and let's add a pop net. Let's connect the circle into the first input of the pop net, and let's dive inside, and here onto the pop source we are using the first context geometry, and the emission tab is set to scatter onto surface. So let's bring up the play bar and enable the real-time playback and hit play, and here as you can see we have particles generated onto the surface of our circle. Okay, so get this particle moving, let's add a force. So right click here, add a pop force node, and let's connect that, and here onto the pop force we have the option to set the force in the X, Y or in the Z direction. So let's add a force into the Z direction. Okay, and hit play, and here as you can see now we have particles moving into the Z direction. We can also introduce noise into our force. So right now we have a uniform force in the Z direction. So here onto the noise, let's increase the amplitude, change this to 1. So now we have a noise applied. Okay, and here we have a force pop wind. Okay, so the pop wind has exactly the same parameter as we have with the pop force. So the difference between these two are that the pop force is an acceleration force. Okay, so here if I add a pop color node, let's add a pop color and connect that, and the color is set to constant. Let's change this to ramp. So here we are using this vex expression to control the ramp. So right now our ramp is using the n age, which is the normalized age of our particles. Okay, so when the particles get older, they will get a white color, and the range is currently set to 0 and 1. And if we go into the pop source and onto the birth tab, we have a very high life. Okay, so let's lower the life. Let's change this to 1 and hit play. And here, as you can see, now we have a gradient onto our particles. Let's increase the life. Let's change this to 2 and hit play. Okay, so that's what the ramp is. Or we can click on this drop down button, and here we have some presets to control the ramp. Let's choose the speed preset. So now we are using the speed of our particles to set the color. Okay, so here we are using a length function. Okay, so we are calculating the length of our velocity vectors, okay, to calculate the speed. So now let's hit play. So here, as you can see, the faster particles will have a color of white. So let's click on this gear icon. So here we have some presets for the ramp. So let's choose the infrared preset. Okay, and hit play. And let's increase the range. Okay, so the faster particles will have a red color. Okay, so let's go back onto the pop source and let's increase the life value and hit play. And here, as you can see, the particles are getting accelerated by the pop force. And if I connect the pop wind, and let's disable the pop force node by clicking on this bypass button, and here onto the pop wind, let's give a 2 value in the Z direction, and let's also add a noise by changing the noise amplitude to 1. Okay, and here, as you can see, the pop wind is a uniform force, so now the particles are not getting accelerated. Okay, so let's go into the pop color and let's decrease the range and hit play. And here, as you can see, we have a pretty much even distribution of our color ramp. Okay, and if I disable the pop wind and let's enable the pop force, and here, as you can see, now our color ramp looks very different because the particles are getting accelerated over time. So you can use the pop force node to create a gravity, and in the top we have a gravity force node. Okay, and the gravity force node, we have the value set to the -9.8, which is the physically accurate gravity value. Okay, and this node is designed to work with all of the solvers that are available in DOPS. Okay, so this gravity force work with the pyro solver, smoke solver, as well as the pop solver and other solvers as well. Okay, and it has a gray input, so which means you can't connect this here, and here as you can see the pop solver is throwing an error. So if you are using this gravity force, you must connect it here. Okay, so here where we have the gray input, or we can connect this here and the gravity force will still work. Okay, or we can copy this gravity value -9.8 and use this here onto the pop force node. Let's zero out the z value and let's add a -9.8 here in y. Okay, and let's remove this gravity node, and here as you can see we have a same gravity force applied to our particles. Okay, let's add a pop limit node and let's connect that. So here onto the pop limit we are defining the limit to where our particles are allowed to live. Okay, so here we have the box, and here you can adjust the size of the box. So if I hit play, and here as you can see the particles outside of these boundaries are getting killed, because here we have the kill outside open boundaries option checked on. So we can close these boundaries by clicking on this closed option. Okay, and here we have the velocity behavior. We can change this to bounce and hit play, and here as you can see now the particles are bouncing. Okay, so let's remove the gravity value and let's add a 2 in the z direction and hit play. And here as you can see the particles are colliding with these boundaries of this box. Okay, and here onto the pop limit we can also uncheck any of these axes. So let's say if I want to escape the particles from the top side of our box, I can uncheck the positive y and let's hit play. And now as you can see the particles outside of these boundaries are getting killed because the kill outside open boundaries option is on. So let's uncheck that, and now let's hit play. And here as you can see the particles are escaping from the top. Okay, so you can use the pop limit node to limit the area of your particles. Okay, and we also have a node called pop kill. So let's connect that, and let's remove the pop limit node, and here onto the pop kill we have the option to use the bounds, and let's enable that. Okay, so here we have the bounding type set to bounding box. Okay, so let's invert this. So now the particles will only live inside of this box. Okay, and outside of these particles will get killed. Or we can uncheck the invert and let's change the center of our box. So now when the particles enter the box they will be deleted. Okay, or we can disable that, and here we have the option to randomly delete the particles. Okay, so let's enable that. So now we are randomly removing the particles. Okay, and we can also increase the chance. Okay, and here onto the pops we have a force called pop attract. So let's connect that, and let's remove the pop kill node, and here onto the pop attract we can attract the particles onto a goal position. So the attraction type is set to position, and here we can specify the attraction position. Okay, so let's increase the position in the z-axis and let's hit play. And let me remove the pop force node. Okay, and hit play. And here, as you can see, the particles are being attracted to that location. Or we can use the points. Okay, so by using the points we can define our own attraction geometry. So let's create that. Let's go back, and in here let's add a sphere, and onto the sphere let's change the primitive type to primitive. So now we have a 1 point. Okay, so let's add a transform node and connect the transform to the sphere, and let's adjust the position of our sphere. Okay, and now let's connect this into the second input and dive inside, and here onto the pop attract we can use the swap path. So if you click on this option you can choose the geometry, or we can use the second context geometry. Okay, and now let's hit play, and here, as you can see, the particles are being attracted to our sphere location. Okay, so here onto the pop net let's add a pop drag. Let's connect that. So the pop drag will add a resistance to the velocities. Okay, so this will slow down the motion of our particles, and let's hit play. And here, as you can see, now all of our particles are being attracted at the location, but the speed is slow. So let's go into the pop attract, and onto the force tab let's increase the force scale. Okay, so now we have a very strong attraction force. So all of the particles are being attracted at the same location. Okay, so now we have much more particles at the single point. So let's add a pop interact node to add the interaction between the particles. Okay, so let's connect that and hit play. And now here, as you can see, the particles are getting attracted to the location, as well as they are now interacting with each other, so they are not getting rams into one another. Okay, and here onto the pop interact we have the options to set the core radius. So let's increase the core radius and hit play. Okay, so now they are maintaining their radius. Okay, and let's also enable the pop wind, and let's zero out the wind velocity. So let's only use the noise to add an interesting movements to our particles. Okay, we also have a force called pop flock. So the pop flock will simulate the bird's flocking behavior. Okay, so let's connect that and let's hit play. And if I zoom in into the location, and let's go into the pop color node, and let's change the ramp to grayscale. So now here, as you can see, we have the flocking behavior. Or let's disable the pop attract node and hit play. And let's also go back onto the pop force, and let's disable the constant activation by changing the constant activation to 0, and here onto the impulse count, let's increase this to 1000. Okay, so the impulse count means that the 1000 particles will generated every frame. So here onto the impulse activation, let's add an expression, say $F. So if the current frame is equal to 1, okay, so now we are only generating particles at the first frame, and let's hit play. And now here, as you can see, we have these 1000 particles, and we have the flocking behavior applied into our particles. Let me increase the overall duration of our timeline. So here onto the range where it says 240, let's change this to 600, and let's hit play. Okay, and here onto the pop flock node, we have the option to choose the number of centers. So let's change this to 3. So now we will have a 3 cluster of the particles. Okay, and here onto the pop interact, let's disable the pop interact node. Okay, so here, as you can see, now we have a 3 cluster of birds flock. Okay, and let's also go on to the pop wind. Let's increase the noise amplitude. Let's change this to 5. So the amplitude of 5 is maybe too much. Let's change this to 2. And let's also increase the number of particles. Let's go into the pop source node. Let's add another 0. Okay, so that's the pop flock node. Now let's talk about pop access force. So let's create a geometry node, tab inside, and in here let's add a circle, and let's change the orientation to ZX plane, and let's increase the division to create a more smoother circle, and let's add a pop net, and let's dive inside the pop net, and here onto the pop source, let's go into the birth, and let's increase the birth rate. Okay, and in here let's add a pop access force. Let's connect that, and here onto the pop access force we have the guide. So the type is set to sphere. We can change this to torus. Let's change this to sphere. So here you can define the axis direction. Okay, so right now we are using the y-axis. Okay, and it will apply the rotation onto the y-axis. So if we go on to the speed, here we have an orbital speed. Okay, so here if I hit play, here as you can see our particles are rotating around the y-axis. Okay, so let's increase the orbit speed, and here as you can see we have the particle rotation around the y-axis. So let's enable the play bar and enable the real-time playback, and after the pop access force let's add a pop drag, and let's connect that. And here we also have the option to lift the particles around the y-axis. So if I increase the lift speed, Here, as you can see, now the particles are moving upward as well as they are rotating. Okay, so let's add a pop color to color these particles, and let's use the color type to ramp and use the speed to color our particles. Okay, and onto the pop access force, let's go into the shape tab and let's change the center and move the sphere up, and let's increase the radius as well as height, and let's hit play, and let's go into the speed tab and let's enable the suction to suck the particles inside of the sphere. Okay, so let's increase the suction speed. Maybe the suction speed it is too high, so let's change the suction speed to 1 as well as the orbit speed to 1. Okay, and let's go into the pop color and let's adjust the speed range, and also let's add a noise into our particle velocities. So let's add a pop force node and let's connect that, and here onto the pop force let's increase the amplitude. Let's change this to 0.5 and hit play, and here as you can see now we have a tornado like particle simulation. Okay, and let's go into the pop source node. Let's lower down the birth rate as well as the life. Let's change the life to 3 and also add a variance of 1 and hit play. Okay, and here onto the pop access force we have the suction. So the suction can have a positive or negative value. Okay, so if I add a negative section, now particles will move outward. Okay, so let's zero out the lift speed and let's hit play. Okay, so now our particles are facing an outward force from the center. Okay, and let's go into the pop force and maybe let's animate the constant activation. So here onto the constant activation let's add an expression $F. So if our current frame number is less than 24, okay, so basically we are emitting the particles for only 24 frames. Okay, and here as you can see we have a shockwave like effect. So let's increase the number of particles to add more particles. Okay, so you can create many cool effects with the pop access force. Okay, and we also have pop curve force. Okay, so the pop curve force will move particles along a curve. Okay, so this node require a curves geometry. So the geometry source right now is set to SOP, which means we can choose SOP geometry. Okay, so let's go back and let's create a curve. So let's add a helix node. Now let's connect this into the second input and let me template the helix, and here onto the helix let's adjust the height and let's lower the turns, and also let's go into the transform and let's translate this in the X to the center. So we have the starting point of our curve to the center. Okay, and now let's go back into the pop net and onto the pop curve force. Let's use the second context geometry as a curve. Okay, so here we have the guide of our curve. So we can go into the guides, and here we have the guide spacing. So let's increase the guide spacing, and also onto the curve force we have a max influence radius. Okay, so that is the influence radius. So the particles that are in this radius will get affected. Okay, so let me disable the pop axis force. So now we only have the pop curve force, and let's hit play. So here as you can see, our particles are moving along the curve. So the speed is slow. Let's go into the pop curve force, and let's increase the follow scale. Let's change this to 5 and hit play. Okay, so here as you can see, some of our particles are escaping, and that is because of this ramp. So here we have the follow scale, and we also have the ramp for the follow scale. And here as you can see, we have a very strong force from the start, and it is fading out. So let's select the last point of our ramp, and let's increase its value to 1 to create an even follow force, and let's hit play. And now here as you can see, we have an even force, but they are still escaping. So let's increase the section scale, and also onto the section force fall off we also have a ramp. So let's set this ramp to 1, so we have an even section force. Okay, and let's hit play, and let's increase the section scale to 2, and let's also lower down the follow scale, and let's change this to 2. Okay, so now our particles are following the curve. So the section scale of 2 may be high, so let's change this to 1 again and hit play. And let's go into the pop source node, and let's remove the constant activation keyframes by right click and say delete channel. Okay, and let's lower down the constant birth rate and hit play. So now we will have a continuous stream of particles. Okay, let's go back here onto the helix. Let's increase the height. Let's template the helix, and let's also increase the turns as well as increase the radius a bit more. And let's go back and hit play. Okay, so now some of the particles are escaping from the start. So let's go into the pop curve force, and let's increase the influence radius to capture all of our particles in the curve radius, and let's hit play. And you can also disable the guides. So if you go into the guides, and let's uncheck the show guide geometry. Okay, so now we don't have the curve visualizer guide. Okay, and let's go on to the pop color and adjust the ramp range. Okay, let's go back onto the pop curve force, and let's increase the orbital scale. So this will add an orbital rotation. So let's change this to 2 and hit play. And now here as you can see, our particles are orbiting around the curve as well as following the curve. Okay, So let's go back and adjust the curve again, and let's bring this onto the center. So here onto the translate, let's translate in the Z direction. Okay, so now let's check. So let's go into the pop source node and let's increase the life value and let's hit play. Let's go into the pop curve force and let's increase the follow scale. Let's change this to 3. And also let's go into the pop force node and let's increase the noise amplitude. Let's change this to 1. Okay. Let's increase the noise amplitude a bit more. Let's change this to 2 to add the noise into our velocity. And also let's increase the section scale. Let's change this to 2. Or maybe let's change this to 1.5. Okay, so that's the pop curve force. Okay. Now let's see how we can create our own custom particle forces to drive our particle simulation. So let's add a geometry node and dive inside, and in here let's add a VDB node to create a vector VDB volume. So here we have the VDB node. Here we can define the VDB name. So let's name this to vel for velocity, and velocity is a vector. So here onto the type, let's change this to vector float, and here we can set the voxel size of our VDB. And if I middle click, here as you can see we have one VDB named vel and it is a vector VDB. So right now, so because VDB is sparse, so we need to activate these voxels. Okay, so for that let's add a VDB activate node and let's connect that. And for the activation, let's use the reference geometry. So for the reference geometry, let's create a box. Here we have a box. Let's increase the box size and let's connect this into the second input of VDB activate. And here onto the VDB activate, let's choose the reference option to activate the region with these box. Okay, and here as you can see we have these volume initialized with the fog. So the default value is set to 1, so that is why we have a fog. So let's disable that. So now we have the VDB volume and now the voxels are empty. So let's fill these voxels with the velocities. So for that let's add a volume warp and let's connect that. And here onto the volume warp, let's dive inside, and in here you can create any noise that you want to create the velocities. Okay, so let's add a curl noise, and onto the position let's use the current voxel position for sampling the noise, and let's write out this noise into our velocity volume by adding a bind export node. And onto the bind export, let's change the name to vel and let's connect the noise into the bind export node. And here as you can see we have some noise fog. So let's dive inside. Here onto the curl noise, let's promote these parameter. So right click on the curl noise, add on to the wax warp option, create input parameters. Okay, so now this will export all of these parameters into the geometry level. Okay, so now here we have these parameters promoted. So to visualize these velocity vectors, we have a node called volume trail. So let's add that. So volume trail node has two inputs. So one is the velocity volume, so let's connect that, and it needs the points to trail. So for that, let's add a points from volume node, and let's connect our box into the points from volume. So the points from volume will generate points inside of our geometry. Okay, and now let's connect these points into the volume trail node and set the display flag to the volume trail. And here we have these velocity vectors. So here we can, onto the volume warp, we can adjust the noise parameter, we can adjust the noise frequency, also we can change the noise type, and we can adjust the noise amplitude. And here as you can see, the amplitude is not visualized correctly, and that is if we go into the volume trail, set the advection method to advect by time. And now if we change the amplitude, here as you can see, now the amplitude is visualized correctly. So now let's see how we can use these velocities to drive our particle simulation. So let's create the particle system. So let's add a sphere, and onto the sphere let's lower the uniform scale down, and also add a pop net. Let's connect the sphere to the pop net, and onto the source let's increase the birth rate. And here as you can see, we have these particles, and to use these velocity volumes, we have a node called pop advect by volumes. So let's connect that. Here we can define the SOP path for our velocity volume. Let's use the second context geometry, and let's go back, and in here let's connect this velocity volumes into the second context of our pop net, and let's hit play. And here as you can see, we have these particles moving with these our custom velocities. And here we have the advection type. Advection type is set to update force. Let's change this to update velocity. And here as you can see, our particles are moving. Okay. Now let's create our own custom pop curve force with these volume velocities. So let me bring all of these setup into the side, and in here let's add a helix to generate the curve. And onto the helix let's lower the number of turns to 1, and let's also increase the size height of our helix, and let's bring this into the center. So let's add a match size node, and onto the match size, justify y, let's change this to none, and justify x, let's change this to max. So now we have our helix at the origin, and let's go back onto the helix node, and onto the output attribute let's enable the tangent attribute. So the tangent attribute is stored in n in the point normal. So if I enable my point normal display, here as you can see, we have these blue vectors that is following the curve. Okay, and if you are using your own hand-drawn curves, so to generate these tangent vector, you can add an resample node, and here onto the resample node we have the option to output the tangent attribute. So let's enable that. So now it is storing in the attribute name tangent u. So let's change this to capital N for the normal. So now we are storing these tangent into the point normal. So if I disable these tangent, and here as you can see, we still have these tangent vectors. or you can also generate this with the orientation along curve node. And let's connect that. Here onto the orientation along curve node, we have the option for the tangent, and it is already set to n. And here, as you can see, we have these tangents. Okay, so because we are using helix, let's remove that, and let's enable the tangent that are available on the helix node. So let's enable that, and after that, let's add a polywire to give him a thickness, and let's connect that, and let's enable the divisions. And here, as you can see, the polywire is inheriting these normals. Okay, so we still have these tangent vectors. Okay, and here let's increase the thickness by changing the wire radius. And to convert this into velocity volumes, let's add a VDB from polygon node, and let's connect that. And here onto the VDB from polygon, we are generating the surface VDB, so let's disable that. And to use this tangent as a velocity volume, so here onto the surface attribute, click on the plus icon, and from the attribute, let's use our point normal. Okay, and let's name this VDB to vel for velocity. So if I middle click, here as you can see, we have these velocity volumes. Okay, and to visualize this vector, let's generate some points by adding points from volume, and add the points onto the polywire, and let's add a volume trail node, and let's connect. This is our velocity volume, these are the points, and here as you can see, we have these velocity volumes. Okay, so now if I connect that into the second input and hit play, here as you can see, we have these particles following the curve. Okay, so right now our velocities are very smooth, so let's add a noise to noise up these velocity vectors. So let's add a volume velocity node, and let's connect that. And here onto the volume velocity node, let's go into the curve noise, and let's add the curve noise, and let's also lower down the amplitude to 0.5. Okay, and the noise is animated. So if I bring up my play bar and enable the real-time playback and hit play, and here as you can see, we have the animated noise. Okay, so let's use this into our second input, and let's check. And here as you can see, we have introduced the noise, and let's dive inside, and in here let's add a pop color node to color these particles, and let's disable the point normal visualization. And onto the pop color node, color type is set to constant. Let's use the ramp, and in here let's choose our speed preset to visualize this color. And onto the speed range, let's increase the speed range and hit play. Okay, so now here as you can see, the particles that are going outside of these velocity regions, they are getting stopped, because after that we don't have these velocity information. Okay, so let's go back, and in here let's add a circle for our emitter. Let's set the display flag to circle, and let's connect that as our emitter. And let's also increase the division and lower down the scale of our circle, and let's hit play. Okay, so here as you can see, we have these particles stopping. So let's go into the VDB from polygon node, and in here let's add the exterior band voxel to add the padding. So let's add the padding of the trend voxels, and let's hit play. Okay, and we still have these particles after reaching the location, so they are getting stopped. So what we can do, we can remove these particles that are outside of this region. So for that, let's go into the VDB from polygon, and let's enable our surface VDB, and let's split these two volumes. So if I middle click, now we have two VDB volume, we have the surface and the velocity. So let's split them, and let's remove these, we don't need that. Visualizer, and in here let's add an split node and connect that, and here onto the split let's choose our velocity field. So on this side we have the velocity volume, and in this side we have the surface VDB. So let's add an null and connect this side, and let's call this one our surface. Okay, and now let's use this surface bound to remove these particles that are outside of this bounding region. So let's go inside the pop net, and in here let's add a pop kill node, and let's connect that, and here onto the pop kill let's choose the bound and enable the bound. Bounding type is set to bounding box. Let's change this to bounding volume, and in here let's select our surface null, hit accept, and here as you can see the inside of these bounds the particles are getting deleted. So let's invert that and hit play, and here as you can see the bounds are aggressive. So let's increase the ISO surface value, let's change this to 0.8 and hit play, and here as you can see when the particles leaves our boundaries they get deleted. Okay, and let's go into the pop color, let's increase the speed range. Okay, and you can also import these velocity volumes in jobs with the field force. So in the job we have a field force. Okay, so this field force works with most of the solvers that are available in the jobs. So it's not specifically designed for pop solvers, so you can use this field force with the pyro solver, smoke solver, and as well as other solvers. So it has a gray input, so let's connect that, and in here it needs the velocity field. To import the velocity fields we have a node called SOP vector field. So let's connect that, and here onto the SOP vector field we can choose the SOP path. So let's go back, and in the volume velocity let's add an null, and let's connect that, and let's call this one well, and let's dive inside, and onto the SOP vector field let's choose our well null. Here we have the well null, hit accept, and here as you can see here we have the guides for the velocities. So in here let's check the use SOP dimension to use the same dimensions from our SOP level, and here as you can see the velocities are not visualized correctly, and that is because this node works with the Houdini volumes, it's not support the VDB volumes. So let's go back and let's convert this VDB volume into Houdini volume. So let's add a convert VDB node, and let's connect that, and onto the convert VDB the convert is already set to volume. So if I middle click, now we have these into Houdini volumes. So Houdini volumes will create 3 volumes for X, Y and Z. Okay, so now if we go inside the PopNet, and here as you can see we have these velocities visualized correctly. So let's go into the field force and onto the guide. Let's scale down the velocity vectors. Okay, and now if we hit play, and as you can see our velocities are animated, but here we don't have the animation. To import the animation, let's go into the soft vector field, and the default operation is set to initial. Let's change this to set always and hit play, and now as you can see we are importing the animated velocities. And let's disable the pop advect by volume, and onto the field force let's disable the guide geometry and hit play. And here as you can see the force scale is not correct, so let's go into the data option and let's increase the force scale. Let's change this to 10, and let's also enable treat as wind and hit play. And here as you can see basically we have the same effect. Okay, so that's how you can generate your own custom forces. Okay, now let's take a look at the pop replicate node to dynamically emit particles. So let's create a geometry node and dive inside, and in here let's add a circle, and let's change the circle orientation to ZX plane, and in here let's add a scatter node, and onto the scatter let's scatter only 3 points. Okay, here we have these 3 points. Let's add a pop net, and let me disable the point display, and let's dive inside, and here onto the pop source the emission type is set to scatter onto surface. Let's change this to all points, and onto the birth let's add a simple expression, and here let's say $F if our current frame is equal to 1. So we are importing our 3 particles into the pop simulation, and let's add a pop force node, and let's connect that, and let's give a force in the positive y direction, and let's also introduce the noise by changing the amplitude, and let's bring up the play bar, enable the real-time playback and hit play. And here as you can see we have these 3 particles. So let's go into the pop source and disable the guide. Okay, so in here let's add a node called pop replicate, and let's connect that, and here onto the pop replicate we have the option to increase the number of particles, and here we have the life. Okay, so this is the second emitter that will emit particle from the pop source. Okay, and onto the shape tab, right now the shape is set to sphere, so let's change this to point and hit play, and here as you can see our first 3 points are emitting particles, and let's go into the attribute, and right now they are completely inheriting the velocity. So in here let's add the variance to the inherited velocity, and let's hit play. So let's lower down the variance value and let's check. Okay, so now here as you can see the pop force node is affecting both of these our particle stream. Okay, so what you can do, you can enable the group, and in here you can select the stream source first input. Okay, So now this will limit the effect only onto the pop source node. Okay. Or what I like to do when I'm working with the pop replicate, I connect the pop replicate as another source and merge it in here. Okay. And by doing so, now I can connect the forces that I want to affect this stream. I can add the forces in here. Okay, so now this force node will only affect this stream. So into the pop replicate node, now we need to define the input stream to replicate. So we need to connect this reference stream. Okay, so it has to be connected like this. And if I hit play, now here as you can see, our pop force node, this pop force node is only affecting this stream, and this pop force node is affecting this stream. Okay, so currently the pop force is set to 0, so it has no effect. Okay, and it is important that you use this reference stream. Okay, so if you connect this stream, and let me remove the wire from here, and here as you can see the setup looks exactly the same, but let me change the setting here onto the pop replicate and go into the birth. Let's disable the constant activation and onto the impulse count. So this is the number of particles that are being generated per frame, so let's change this to 1. Okay, and now let's hit play. At the frame 55, if I middle click, here as you can see we have 336 points. Okay, so if I connect this into the reference stream, and now if I hit play, and now if you middle click, now here as you can see we have 189 points. Okay, so let's go back, and in here let's only emit the 1 particles. Okay, and let's check, and now let's middle click, and here as you can see we have the 67 points, so we are on the frame number 66. Okay, so before that, if you connect this input, so now we have multiple points on top of each other, and if we middle click, here as you can see we have 134 points. Okay, so it is replicating more points than it needs to, so you have to connect the reference stream into the pop replicate node. Okay, so let's remove this input, and here onto the pop replicate, let's disable the impulse count, and let's enable the constant activation, and also let's increase the number of particles, and let's check. And here as you can see we have these trailing particles, and let's go back. In here let's emit the 3 particle streams, and also let's add a helix, and let's change the helix settings, lower down the turns and increase the height, and also let's add a match size node and bring the helix at the center. So onto the justify y, let's change this to none, and onto the justify x, let's change this to max, and let's connect this into the second input, and in here let's add a pop curve force, and let's connect it there. And the geometry source, let's use the second context geometry, and let's adjust the follow scale ramp and also the suction scale ramp. Okay, and now let's go into the guides and disable the pop curve force visualizer guide, and let's hit play. Okay, let's add a pop color node. After the merge, and change the color type to ramp and choose the speed ramp, and let's also increase the range. And after the pop curve node, let's add a pop drag to add the drag into the velocities, and let's check. Let's disable the pop force node for now, and here onto the pop curve force, let's enable the guides to check if all of these particles are inside of this range. And let's go into the curve force, let's increase the max influence radius and also increase the follow scale as well as the section scale. Okay, and let's go into the pop replicate node and into the attributes. Let's lower down the inherit velocity scale. Let's change this to 0.1. Okay, so now they are following the velocities correctly. And let's also add a pop drag, and let's connect that into the replicate stream and let's hit play. Okay, let's go back. Let's increase the inherit velocity scale. Let's change this to 1 again and let's check. And let's also increase the variance to have the more spreading. Okay, and let's go into the pop curve and disable the guides and also increase the number of particles. Okay, and let's also add the noise by changing the amplitude. Okay, so the amplitude 1 is maybe too much. Let's change this to 0.5. And let's go into the pop replicate and let's adjust the life expectancy. Let's change this to 2 and add a variance of 1 and let's check. Okay, so that's the pop replicate node. Okay, now let's see how we can use the smoke simulation velocities to advect our particles. Okay, so first let's create a smoke simulation. So let's create a geometry node and dive inside, and in here let's add a sphere. And let's add a pyro source node, and onto the pyro source node let's initialize this to source smoke, and onto the mode let's choose the volume scatter to scatter the points inside of our sphere. And after that let's lay down a volume rasterize attribute node, and let's rasterize our density. And after that let's lay down a pyro solver, and onto the pyro solver let's go into the sourcing. So we are using the density into density and temperature to temperature, so let's use our density field as a temperature, and we don't have the burn field, so let's remove that and let's hit play. Okay, so let me open up my play bar and enable the real-time playback, and let's go on to the fields tab, and let's lower the smoke dissipation to a lower value, 0.001, and let's hit play. Okay, now let's go into the sourcing tab, and let's add another field. Let's use our intensity field into the divergence. Okay, so now we are using the intensity field into the divergence to add an expansion. So let's hit play. So let's increase the source scale. Let's change this to 2, or maybe let's change this to 10. Okay, and right now our simulation is fast. So here onto the temperature, let's change the operation to add, and let's add a 0.1 source scale, and let's check. And we still have an fast, so let's lower this down even further, 0.01. Okay, so now we have a much higher expansion. So now let's lower down the expansion scale. Let's set this to 5. Okay, so the scale of 5 is looking good. Let's go into the shape tab, and let's enable the turbulence and set the turbulence scale to 1. Let's increase the turbulence scale even further. Let's change this to 5 and check. So the 5 has too much disturbance, so let's lower this down to 2.5. Okay, so 2.5 value is looking good. And let's also break up our source. So after the pyro source node, let's add an attribute noise node, and let's connect that. And in here, let's change the attribute name. Here is set to vector. Let's choose the float and select our intensity attribute, and let's remove the CD. And the range value, let's change this to 0 centered, and let's check. Let's lower down the element size to 0.1, and also increase the amplitude, and set the operation to multiply. And let me untemplate my pyro source node. Okay, so we do have noise apply because the voxel size is low, so we can't see much. So let's set the display flag to the pyro solver, and let's check. And here, as you can see, we have the noised up source, and let's lower the turbulence down, and let's lower the turbulence down even more. Change this to 0.5. And let's also enable the disturbance and increase the disturbance scale to 10, or maybe let's change this to 5. Okay, something like that. So because we are using this velocity field, we don't need to create a higher simulation. Okay, so let's go on to the output tab, and in here let's remove the temperature field and flame as well as the CD. We only need the velocity field for advection. Okay, And also let's check convert to VDB and use the 16-bit floats. And after that, lay down a file cache, and you can write out your simulation caches. Okay, and after that, let's add a popnet, and let's use the same sphere as an input. Okay, so but now here onto the popnet, we have the option to emit the particle from the surface of our geometry. So because we are using the volumes, let's add the particles inside of our sphere to create more particles. Okay, so after that, let's lay down a points from volume node, and let's connect that. And onto the points from volume, let's lower down the point separation to generate more points. So let's change this to 0.01. Okay, so now we have these particles in the regular array. So let's add an jitter scale to randomize the position. So let's add an jitter scale of 1. Okay, and let's go into the popnet, and let's connect the velocity volumes into the second input. So if you are using the cache simulation, you need to connect the file cache. Okay, and let's dive inside, and in here let's add a pop advect by volume and connect that. And velocity source, let's use the second context geometry, and the field name is set to well, which is correct. And onto the pop source, let's change the emission type to all points, and let's check. Okay, so now we have much more particles. So what I like to do is, if you go on to the display material option, right click and change the particle display option to pixels. Okay, so now we are viewing the particles as a pixel. And also let's go on to the pop source and onto the burst tab. Let's animate the impulse activation. So in here let's add an expression $f. So if our current frame is less than 5, so let's emit particles only for the 5 frame. Okay, and let's check. Okay, so let's go into the pop advect by volume node, and here we have the advection type is set to update force. So let's change this to update velocity, and the advection method, let's change this to trace. So the advection method trace gives the correct result. Okay, and let's check. Okay, so now here, as you can see, we are using the smoke simulation velocities to advect our particles. Okay, and after that, let's add a pop color node to color these particles. Let's connect that and change the color type to ramp, and let's use the speed ramp, and let's check. Let's increase the speed range. Okay, let's play it again. Okay, here onto the pop advect by volume, let's lower the velocity scale. Let's change this to 0.8. And let's also add a pop drag, and let's connect that. Okay, so if I middle click, and currently we have 2 million particles in our sim. So let's go back, and in here let's lower down the point separation to generate more particles. So let's lower this down to 0.005 and let's check. Okay, so because we are only emitting these particles for 5 frame, so let's middle click. Now we have 16 million particles. Okay, so 16 million particles I think is enough. So after that, let's lay down a file cache and let's write out our particles cache to disk. And before that, let's remove all of these attributes that we don't need. Okay, so in here let's add a clean node and let's connect that, and onto the clean node let's check the remove attribute as well as the remove groups. Okay, and here onto the clean node let's uncheck the remove unused points. Okay, and also uncheck the remove degenerate primitives. Okay, so now we have our particles back, and now we don't have all of these attributes that we don't need. So now here onto the file cache let's write out our particles cache. Okay, all done. So I have written out the particles cache, and now let's render this. So before importing into the Solaris, let's add a transform node and let's rotate these particles into 90 degrees in the Z. So let's change this to -90. Okay, so now we have these particles going into the side, and after that let's add a p scale attribute. Okay, so we need the p scale attribute for rendering. So after that let's lay down an attribute wrangle node, and here onto the attribute wrangle node let's create our float f at p scale, and let's create the p scale value of 0.005. Okay, and after that let's add a null and let's call this out. And now let's go into the stage context, and in here let's add a sub import, and let's select our out null. Okay, so here we have these particles imported in Solaris. So let's rename this sub import to particles, and after that let's create a material. So let's add a material library node, and let's dive inside, and in here you can use the principal shader. Okay, so if you are using the Karma CPU version, you can use the principal shader. So but we are going to use the Karma XPU, so we need to add the material X. So let's add a material X standard surface material. Okay, and here onto the material X standard surface let's go into the specular, and let's add the specular roughness to 1, and let's also go into the base color and let's create a darkish gray base color. Okay, and now let's go back and click the autofill button to fill the material slot, and also check the assign to geometry, and in here let's drag our sub import and let's remove the stage. Okay, and after that let's create a light. Let's add a dome light, and onto the dome light let's select the file From here, let's go into the Houdini pick HDRI and let's select the HDRI Heaven Skylight Garage. Hit accept. Okay, so here we have the light. So let's go into the display option and go into the background and let's uncheck the display environment light as background. Okay, and after that let's add a karma wrap. Okay, and set the display flag to the karma, and here onto the karma let's change the render engine to XPU, and let's also increase the exposure for our dome light, and let's choose our karma to render our particles. Okay, so here we have our particles rendered. So let's go into the dome light and let's adjust the exposure a bit more, and also go into the transform node and let's rotate our dome light around the y-axis. Okay, and after that let's create another light. So let's add a light and let's connect that, and onto this light let's change the type to sphere and let's increase the sphere radius, and let's bring this light in front. So let's adjust its transform Z and also increase the sphere radius, and let's change its color to blue, and let's increase its value to create a brighter blue color, and let's also move into the front and also into the X direction, and let's duplicate this light, connect it here, and from this light let's change its color as well as its position here onto the X, and let's also lift him up a bit, and let's see with our render. So let's choose the karma, and to disable these light guide we have the option, so display light guide, let's uncheck that. Okay, and also let's go into the base properties and let's increase the exposure of our light. Let's increase the exposure for the blue light and also for the dome light as well. So let's increase the dome light exposure, and let's also change our background to dark. So click on this I button and change the color scheme to dark. Okay, so here we have our render. So let's add a camera and choose the angle. So let me change this back to Houdini GL and control click on the camera icon to create the camera, and let's lock the camera and select our viewing angle. Okay, and let me hide the shelf, and let's connect the camera before the material library. Okay, or we can add an merge and organize our node graph. So let's connect the merge here and let's disconnect the camera as well as all of these lights. Okay, and let's connect this light into the merge, and let's disconnect them from here and connect it into the merge, this one into the merge as well, and let's also connect the camera into the merge as well. Okay, so now the node graph is look more organized. Okay, it's totally up to you however you want to lay out your nodes. Okay, so there is no right or wrong way. So if you want to render your particles in additive style, so let's go into the material library, and in here let's lay down a material X surface unlit shader. Okay, so onto this shader we don't have the lighting effect, so let's go back onto the material library and let's click autofill material, and we have the unlit material. So let's copy this geometry path and paste onto this assign to geometry path, and let's uncheck this assign to geometry. Okay, so now we are using the unlit material for rendering, so now these lights won't affect our particles. Okay, and let's render this, and here as you can see we have these unlit particles, and for rendering these additive transparent particles we need to adjust the particle scale. So let's go into the object level, and in here let's lower down the P scale value, so let's change this to 0.001, and let's go back and let's check, and here as you can see the render is very fast. So because here we don't have these lighting calculation, so let me disable the grid, and let's go into the material library and onto the material surface. Let's lower down the opacity, let's change this to 0.5. So now we have these transparent particles render. So here onto the emission color, let's choose a lighter blue color, and let's also lower down the saturation value. Okay, and also increase the emission scale, let's change this to 2. Okay, so if you want to create an energy effect, so that's how you can create these additive particle render. Okay, so let's go back, and here onto the Karma render setting, let's choose the resolution, let's change this to 1080, and choose your output picture location and go into the USD render op and change the valid frame range to render specific frame range to render out our 120 sequence. Okay, and press render to disk option to render your sequences. Okay, so rendering has finished, and here is the particles render, and this is our end results. Okay, now let's disintegrate geometry with particles, and for this example I downloaded the model from Polyheaven. So Polyheaven is a good resource for free HDRI and texture as well as 3D models. So from here I downloaded this model marble bust, and from here you can select the file that you want to download. So right now it is selected to Blender. You can here choose the FBX file, and here you can select the maps. So here we have the ambient occlusion, we have roughness metal and diffuse, and you can select the file format. So if you want to download from EXR or JPEG, and press the download to download the model. Okay, and in here let's load our model. So let's create an geometry node, and I'm inside, and in here let's add a file node and load our model. Okay, so the model came in very huge, so let's add a match size, and onto the match size check the scale to fit option to make the model unit scale. So now the size will be 1 by 1, and press F to frame the geometry, and onto the justify Y, let's change this to minimum. So now the model will sit perfectly on the floor, and let's disable the UV visualization by clicking on this UV visualization button. Okay, and if I middle click here, as you can see, we have some attributes, the FPX and the FPX scale. So let's remove all of these attributes that we don't need, and after that let's add a clean node and check remove attribute as well as remove groups, and uncheck the remove tree generate primitive. So I find that the remove tree generate primitive is very aggressive, and after that let's keep the UV attribute for rendering. So after the remove attribute, let's add a hat sign and the name of the attribute that you want to keep. Let's name this UV. So now we do have the UV attribute. So if I enable my UV visualizer, here as you can see, now we have the UV attribute. Okay, and after that let's generate a mask from where we will emit particles. Okay, so for that let's create a sphere, and let me template the sphere, and onto the sphere let's change the primitive type to primitive. So now we have a single point, and let's scale the sphere down, and let's add a transform node and press enter on the viewport to access the transform node manipulator, and let's place the sphere from where we want the mask to start. Okay, so let's place this somewhere. Okay, and after that let's create distance from geometry node, and the distance from geometry node has two input. First one is the geometry for attribute and the reference geometry. Okay, so the distance from geometry node will generate the attribute named dist, and the dist will store the distance of each of our geometry points from our reference geometry. And the reference group type, let's change these 2 points. Okay, and to visualize this, click on this visualizer button. Okay, so here as you can see we have a gradient. So right now the gradient is not very visible, so let's uncheck the visualizer and let's adjust its attribute by lay down an attribute warp node, and in here let's import our dist attribute. So let's lay down a bind node, and in here let's type the attribute name dist, and let's fit range this attribute, and let's visualize this as an SCD. Okay, so here as you can see we have the gradient. So here onto the fit range we can adjust the source max to control the gradient. Okay, so let's promote this parameter source max. So middle click on this input and click promote parameter to promote the parameter, and double click on this input. So here as you can see we have a parameter node. Okay, so let's rename its label. Let's call this one fade. Okay, and after that let's add a ramp parameter to adjust its attribute with the ramp. So let's connect that, and in here let's change the ramp to a spline ramp, and let's go back, and in here let's adjust the ramp. Okay, and here we have the fade to tighten up the fading of the ramp. Okay, So now what we can do, we can add an offset value after we fit range to control the fading. So let's add an add node, and let's create a parameter, and let's connect this and onto the parameter. Let's name this offset, and let's go back. So here we have the offset parameter, so we can adjust the offset parameter so the negative value will control the fading. Okay, and here we have the ramp to further adjust the ramp. Okay, so now let's add the noise into the fading. So let's dive inside, and in here let's add a turbulent noise, and let's use the point position, and let's add this into our dist value. Okay, and here onto the turbulent noise, let's change the noise type to simplex noise, and let's also promote the noise frequency. So come here onto the noise node, middle click on the frequency, and click the promote parameter to promote the frequency. Okay, so here we can adjust the noise frequency, and here we can adjust the fading of the ramp. And now let's animate the offset. So when we have white color, okay, so let's add a keyframe. So press and hold the Alt key and click on the parameter to add a key, and let's go on to the frame 100, and let's adjust the offset until we see all black. Okay, and press and hold the Alt key and click on the parameter to add a key, and let's enable the real-time playback and hit play. Okay, so here we have the fading. So now let's adjust the keyframe interpolation. So right click on the parameter and go into the channel and click on the isolate channel list. Okay, to bring up the animation graph, and let's select all of these two keyframe, and let's change the interpolation from here. Let's change this to linear. So now we have the linear interpolation of the keyframe. Okay, so now let's check. So now let's export this attribute. Okay, so right now we are visualizing this attribute as a color. So let's write this attribute out by adding an bind export node, and let's connect that. And in here let's call this attribute intensity. Okay, and let's go back, and in here let's adjust the gradient. So what I want is a rim that will emit the particles. Okay, so for that let's adjust the ramp. So let's bring this first value down and bring this value to a bit closer. Okay, so now basically we have a rim that will emit the particles. Okay, so now let's add a scatter node, and in here let's enable the density attribute, and let's disable the force total count. Okay, so if you enable the force total count, so when we don't have the density attribute, so when the density attribute is 0, so now the scatter will scatter these points onto our geometry. Okay, because the force total count is on. So let's disable that and enable the density. Okay, so now we are only adding the points where we have the density attribute. Okay, and let's raise the density scale to add more particles. Okay, and let's uncheck the relax iteration, and let's add more points. Okay, so here we have the rim that will emit particles. Okay, now let's set up our particle simulation. So first let's untemplate the sphere, and in here let's add a pop net, and let's connect that, and let's dive inside, and here onto the pop source let's change the emission type to all points, and let's go into the birth tab, and let's adjust the life. Let's change the life to 3 and add a variance of 1, and let's also adjust the global frame range. So let's change this to 120. Okay, and let's go back to the first frame and hit play. Okay, so here we have the particles. So now the particles are not moving, so let's create a particle force. So in here let's create a force that will push these particles outside. Okay, so let's use the point normals for that. So let's add a normal node to create the normal attribute. Let's connect that, and here onto the normal let's change the add normals to points. So if I enable the point normal display, here as you can see we have these normals, and when we scatter the points, the scatter solve will inherit these normals. Okay, so now we can use these vectors to push these particles. Okay, so let's add a point velocity node, and onto the point velocity the initialization is set to compute from deformation. Let's change this to from attribute and use our normal. Okay, so now we do have an AV. Okay, let's set the display flag to the pop net, and let's disable the normal visualizer, and let's go back and hit play. And here as you can see now the force is too strong, so in here let's adjust the scale. Let's lower the scale down to 0.1, and let's check. Okay, so the scale of 0.1 is looking good, and let's go into the curl noise, and let's add a curl noise to our velocities, and let's check. So the noise is strong. Let's lower the scale down to 0.1, and let's check. Okay, so now we have some initial movement. So now let's dive inside the pop net, and let's add a pop force node to add the additional noise, and let's connect that. Let's add the amplitude, and after that let's add a pop drag, and let's connect that, and let's check, and let's lower down the solid size. So the solid size of 1 is too big, so let's lower this down to 0.2 maybe, and let's check. And also let's lower down the amplitude. Let's lower this down to 0.3. Okay, so now let's adjust the particle's life. So the particle life of 3 is maybe too much, so let's change this to 2, and let's check. Okay, so the life of 2 is looking good. And also onto the power force let's add a directional force. Okay, so let's add the directional force in the X. Let's change this to 1 and check. Okay, so now the wind is blowing these particles onto the side. Okay, and right now the particles are inheriting the colors from the soft level. So let's add an pop color node and color these particles with the speed. So let's add an pop color and change the color type to ramp and choose our speed preset, and let's adjust the speed range. Let's go back to the first frame and hit play. Okay, let's lower down the speed range. Okay, and let's visualize these particles as a pixel. So let's go into the material option and onto the particles. Let's change them to pixels. Okay, and here as you can see we have these particles stepping. So because our particles are moving fast, so we have these particles stepping. So let's go into the pop source and let's add a negative jitter burst time and let's check. Okay, so we still have some stepping. So let's go into the pop solver and let's adjust the substeps. So let's change the min and max substeps. Let's change this to 5 and 5. So min and max, both set them to 5 and let's check. Okay, so now we have less stepping. So maybe let's change this to 3 by 3 and let's go into the pop force node and let's lower the force scale. Let's change this to 0.3 and let's check. Okay, let's go back and in here let's view this with our original geometry. So to remove the geometry with the particles, let's duplicate this attribute walk. Okay, and in here let's reset the ramp. So right click and change revert to default. Okay, so now we have the ramp. Okay, and after that let's add an blast node and in here let's add an expression. So let's say where we have the intensity attribute less than 0.1. Okay, so which means where we have the black color, the geometry will get deleted. And we also change the group type. Let's change this to points. Okay, because the intensity is a point attribute. Okay, so here as you can see now we are removing the geometry, and after that let's add a clean swap, and in here let's remove the attribute and the groups, and also let's add a hat sign. We want to retain the UV attribute. Okay, and let's visualize the UV. So here we still have the UV. Okay, so let's uncheck that and let's add an merge and let's merge this with our particles. Okay, now let's write these particles out. So before writing these particles, let's add a clean swap to remove the attributes that we don't need. Okay, in here let's check the remove attribute, remove groups, and uncheck the remove unused points as well as the remove generate primitives. And in here let's keep the age attribute. So after that let's add a hat sign and let's keep the age attribute. So if I middle click, now we do have the age attribute. Okay, and now let's add a file cache and let's write these particles out onto the disk. Okay, so I have written out all the caches. So now let's use the age attribute to color our particles as well as set our p-scale attribute. So let's add a color node and connect it here. And onto the color, let's change the color type to ramp from attribute and use our age attribute. And here we can adjust the range. So let's adjust the range. And onto the first, let's choose the darkish brown color. Okay, and up here let's create a lighter brown color. Okay, and after that let's lay down an attribute warp node and dive inside, and in here let's remap our age attribute to set the p scale. So let's add an fit range node and let's connect the age into the value and here onto the fit range. So let's use the range from our color, so 0 to 2. So let's dive inside. Source minimum is 0, source max is 2, and we want the particles to have a higher scale value when they bond. So into the destination min, let's add a scale of 0.001, and I want the scale to fade out as the particles gets older and die. So onto the destination max, let's zero out the p scale value. Okay, and now let's write this attribute out as an p scale. So let's add an bind export node and let's connect that, and let's call this one p scale. Okay, and let's go back, and after that let's create a null and let's call this one out particles, and let's come over here. So that is our geometry. So let's remove the merge, we don't need that, and after that let's add a null here as well, and let's call this one out geo, and let's go into the stage context and let's add an SOP import node, and in here let's import our out geometry and let's call this one geo, and let's duplicate this SOP import node, and in here let's import our particles and let's call this one particles, and let's merge both of them. And let's add a dome light for lighting. Now let's merge this, and onto the dome light let's select a file. So let's go into the Houdini pick HDRI and let's select our skylight garage. Okay, and let's set the display flag to merge. So here we have the particles, geometry and the light. And now let's create the material. So let's add a material library and connect it there, and let's dive inside. So in here let's add a material X standard surface, and let's call this one geo, and let's duplicate this material, and this one let's call this particles, and for geometry let's import our diffuse map that we have downloaded. So in here let's add a material X image node to load the image, and onto the file name let's select our diffuse map. Let's load the marble bust diffuse. Okay, and let's connect this into the base color of our material X. Okay, and for particles to use the CD attribute, so if we go back here onto the particles, here as you can see we have the CD attribute. So when we created the color node, so it creates the CD attribute. Okay, so let's use this attribute to color our particles. So let's go into the stage context, and in here to import the CD we have a node called UST primvar reader. Okay, so the CD in the UST is called the display color. Okay, so let's type display color. So the C is capital. Okay, and it is a vector attribute, and let's connect this into the base color of our particles, and onto the specular let's increase the specular roughness. Let's change this to 0.8, and let's go back, click on the autofill material to fill the material slot, check the assign to geometry, and let's drag the geometry node into the geo material, and let's remove the stage. And for the particles let's assign the particles geometry node and remove the stage. And after that let's add a karma render node, and onto the karma let's change the render engine to XPU, and from here let's select the karma to render the particles. Okay, so let's adjust the lighting. Let's go into the dome light, and let's increase the exposure, and let's hide this light visualizer. So click on this light guide, and also let's hide the light for the background. In here let's uncheck the display environment light, and also let's change the viewport to dark, and also let's disable the grid. Okay, let's choose another frame. So here as you can see we have the geometry with the texture applied correctly, and here we have the particles that are disintegrating the geometry. Okay, so from here let's select the camera angle and create a camera, and let's position the camera into the camera region, zoom our geometry in the camera region. Okay, and let's hide the shelf, and let's bring the camera here and disconnect it from there, connect it into the merge. Okay, and let's render out the sequence. Okay, now let's talk about grains. Grains are used to create the sand and snow simulation. Grains can also be used for soft body simulations as well. So let's see how we can set the grains up. So let's create a geometry node and dive inside, and in here let's add a file node, and let's load our marble bust geometry. Okay, so the model comes in a very large size, so let's add a match size node, and onto the match size let's check scale to fit, and onto the justify Y let's change this to minimum to sit the floor, to make the model sit onto the floor. And onto the target size let's increase its size by change this to 3 by 3. Okay, and let's disable the UV visualization, and after that let's add a clean sub to remove any unwanted attributes. So let's check remove attribute and remove groups, and after that let's lay down a grain source node. So let's connect that. Grain source node will generate particles inside of our geometry. Okay, and to better visualize these grain particles, come over here into the display material option and onto the particles. Let's change the particle display to lid sphere. Okay, so here we have the particles and they have the P scale. So here onto the point separation we can adjust the number of particles. Okay, and let's add a pop net, and let's connect that, and also dive inside here onto the pop source. Let's change the emission type to all points, and onto the birth let's add an expression $FF if our current frame is equal to 1. So $FF means that when we change the substeps in our pop solver, so if I enable the play bar and enable the fractional frames, and if I zoom in into the timeline, and here as you can see we have some between frames, so 1, 1.1, 1.2. okay, so when we increase the substeps, so these between frames will be calculated, and by using the $FF this expression will evaluate correctly. Okay, so it is always a good idea when you are in DOPS, use the $FF. Okay, so let's go back and disable the fractional playback, and let me reset the zooming of the timeline, and let's also enable the real-time playback. And in here to simulate these grains, let's lay down a node called pop grain. Okay, so let's connect that. So now we have the pop grain, and if I hit play, so nothing happened. So let's add a gravity force, and let's connect that. And now if I hit play, here as you can see the particles are falling due to the gravity. So let's add a ground plane for collisions. So in here let's add a ground plane, and let's add a merge node and merge it here and connect the ground plane. So here onto the merge node we have the effector relationship, so the left input affect the right inputs, so we can change this to mutual. Okay, so now let's hit play, and here as you can see our grains are colliding with the floor. And let's also go into the pop source and disable the guides and hit play. Okay, and now let's color these particles. So let's add a pop color node and connect that, and here onto the pop color let's change the color type to ramp, and from gear icon select the sand preset, and this time let's randomize this ramp. So in here where ramp is equal to n age, so in here let's add an expression rand. So rand is an fx function, and in here let's add an add id attribute. So each particles have a unique id. Okay, so now the rand function will generate the random value 0 to 1 range. Okay, and here we are using the ramp to set the random colors. Okay, and let's check. Okay, let's go into the pop grains, So here onto the pop grains, we have the particle separation. So this particle separation must be linked with the grain source point separation. Okay, so let's connect that. Let's copy this parameter, and in here let's paste this relative reference. Okay, and let's dive inside. And second, we have the constraint iteration. So constraint iterations are used to solve these particles collision. Okay, so the more constraint iterations you have, the accurate of your simulation will be. Okay, and whenever you are working with grain, go into the pop solver and set the min and max substeps to 10. Okay, so the grains will produce accurate result when they have enough substeps. Okay, so when you are working with grain, start with 10. Okay, and let's check, and let's go into the pop grain. So by adjusting the particle separation, we can generate more particles into sim. And here we have the friction. So the friction with the colliders, so this the collision plane, and with the particles themselves. Okay, and also we have the scale kinetic. So this is essentially a drag into the particles force energy. Okay, so here if I hit play, here as you can see the particles are sliding onto the floor. So if I increase the scale kinetic, let's change this to 0.5, and now here as you can see they are losing the energy and they are not sliding as much. Okay, and we have the internal collision. So the collision of the particles, we can turn off the collision. So if I set the weight to 0, so now we don't have any collisions between particles. And if I hit play, here as you can see we are losing our volume because we don't have the collision between particles. So let's set this to 1, and here you can control the stiffness of these collision. And we have the mass shock scale. So this is the repulsive force, so when the particles collide, so in which direction they push apart themselves. Okay, so here we can define the direction. So if I change this x to 1, and let's zero out the y, and let's also increase the scaling factor. Let's change this to 100, and if I hit play, and here as you can see now the particles are pushing themselves in the x direction. Okay, so most of the time you will be using the y-axis. Okay, so let's change this to 1 in y. Let's zero out the x-axis and set the power to 1. And after that we have the clumping. So the clumping will use to create the dry sand, wet sand effect. So right now the clumping weight is 0, so which means now we have the dry sand effect. And if I change the weight to 1, and let's increase the stiffness, now we here as you can see particles are sticking together. So let's change the stiffness to 10, and let's check. Okay, so let's go back, and here onto the grain source, let's add a rotation. Let's rotate our source in the z-axis. Okay, let's rotate this 145 degrees and also move the source up. Okay, and let's go back and check. Okay, so here as you can see now the particles are sticking together. So onto the scale kinetic, let's change this to 0.1. Okay, So that's the clumping. So let's zero this out, and here we have the option for the explicit constraints. So this is used for when you have these constraint. So let's go back and here onto this grain source and come into the explicit constraint and click on the create option to create the constraint, and let's increase the search radius. Okay, and here as you can see we have these lines that are connecting these particles. So these are the constraints. Okay, so let's go back onto the PopNet, and to import the constraint geometry we need to go into the pop source and onto the source. Let's change the emission type to all geometry. Okay, so now here as you can see we are importing these constraints as well. So let's go into the pop grain and onto the explicit constraint. Let's change the weight to 1. Okay, so now we are using these constraints, and let's hit play. And here as you can see we have this bouncing soft body simulation. Okay, so let's go back, and in here we can adjust the constraint stiffness, and also we can enable the constraint breaking. Okay, so let's check, and here as you can see we have these constraint breaking effect. So the constraints are now breaking. Okay, and when we are importing the constraint geometry inside the DOBs, so the visualization of our sphere doesn't work correctly when we are in the DOB, so it may be some bug. So let's go into the geometry. In here let's pin this viewport to geometry level. So now when we are in the PopNet our viewport is pinned down to the geometry level. Okay, and here we can see the particles correctly. Okay, and let's zero out the explicit constraint, and let's go back here onto the grain source. Let's uncheck the constraint geometry. Okay, and in here we have the clumping, so we can set this clumping weight attribute randomly onto our source particles to create a clumps of wet sand. Okay, so the attribute is called the attraction weight. So let's go back, and in here let's add an attribute warp node, and let's connect that and dive inside the attribute warp node, and in here let's add a turbulent noise, and let's connect that into the position, and let's connect this into the CD to visualize the noise, and let's adjust the frequency and also increase the amplitude. Okay, and let's lay down on a bind export node, and let's write this attribute out. So the attribute is called the attraction weight. Okay, and let's go back, and in here, so now this weight will be multiplied with our attribute, so let's set this to 1. Okay, and into the pop color let's visualize our attraction weight. So in here let's add a double slash to comment this out. Okay, so by adding the double slash we can create a comment. So now this line will not evaluate any function. Okay, so now it is comment out. So in here let's add a ramp is equal to our attraction weight attribute. So in here let's add attraction weight attribute. Okay, and let's change the color to grayscale. Okay, so here we have the attraction weight, and let's go into the pop crane and let's lower the particle separation. Okay, and also onto the pop solver. So the substep is set to 10, which is good, and let's check. Okay, so now our particles are sliding too much, so let's go into the pop crane and increase the scale kinetic. Let's change this to 0.5 and let's check. Okay, so here as you can see, our particles that have black color is in a dry sand, and the white particles are wet sand clumps. Okay, now let's see how we can activate the grains with the attribute. Okay, so let's go back in here. Let's create an activation attribute. So first let's remove the transform node. Okay, so now we have our first sitting at the floor. Okay, and in here when we added the clean sop to remove the attribute, so let's create a growing attribute that will activate our grains. So for that, let's add a distance along geometry node. Okay, and let's connect that, and here onto the distance along geometry node. So here we have the option to specify the start point. Okay, so let's pick up the start point where we want the attribute to start grow. Okay, so maybe let's select this point and press enter. Okay, so now it will generate an attribute, growing attribute. Okay, so it will calculate the distance of each geometry point from our this reference point. Okay, so if I enable the distance, so basically we have a gradient. Okay, and now let's add an attribute warp node to adjust the attribute. Okay, and let's dive inside, and in here let's bind import our dist attribute, and let's also add a fit range, and let's connect the dist into the fit range, and after that let's connect this into the CD, and in here we can adjust the source max to tighten up the gradient. Okay, and to animate this, let's add an offset. So let's add an add node, and onto the distance let's add an offset. So in here let's add a parameter node and connect this, and let's call this one offset, and let's go back, and here we have the offset. Okay, so the negative value will grow the attribute. Okay, so here as you can see we have the black gradient spreading, so but we want the inverse of that effect. Okay, so let's dive inside, and in here after the fit range let's add a ramp parameter, and let's connect that, and onto the ramp let's change the ramp type to spline ramp, and let's go back, and in here let's select this first input and give him a value of 1. Okay, so now we have the reverse effect of our gradient. Okay, and let's animate the offset. So let's change this when we have the all black, so alt click to add a key, and let's go on to the frame 100, and let's change the offset value. Okay, and alt click to add a keyframe. And also let's adjust the keyframe interpolation. So right click, channels, and isolate channel list. And in here let's select these two keyframe and choose the linear interpolation. Okay, so here we have the attribute that is growing. So let's dive inside and let's find export this attribute, and let's call this attribute active. Okay, and let's go into the grain source node, and here as you can see the grain source node is not inheriting these attribute. So let's add an attribute transfer node to transfer the attribute, and let's connect that and transfer the attributes from this attribute warp node and onto the attribute transfer node. Let's uncheck the primitive and let's only select the active attribute. Okay, and to visualize if our active attribute is working, so let's click on this I button and click on this active to add a visualizer, and let's hit play. And here as you can see we have the active attribute growing. Okay, so let's click on the eye icon and click on the active to hide the visualizer, and after that let's connect this into the attribute warp node. So here we are generating the attraction weight. Okay, so let's go into the popnet and dive inside, and here as you can see our active attribute has not been imported. So the active attribute is only imported onto the first frame, so the animation that we have onto the active attribute will not be computed inside of the popnet. Okay, so because onto the pop source we are only initializing our geometry onto the first frame. Okay, so to import our animated attribute, let's lay down a pop wrangle node. Okay, and let's connect that, and here onto the pop wrangle let's go into the input, and onto the input 1 let's use the first context geometry. Okay, so this geometry, and let's go into the pop wrangle code, and in here we have an attribute that grains understand, and it is the mass. So it's a float attribute, so float attribute name mass. Okay, so if the particles have no mass, then no force will affect the particles. Okay, so which means the particles will stand still if they have no mass. So let's use the active attribute to set the mass. Okay, so to import the attribute from SOP, let's add a point function. Okay, and if you click on this function and press F1, this will open up the help for the point function. Okay, so here we have the point function. This reads a point attribute value from a geometry, and here we have the type that we need to specify. Okay, so because the active we created a float attribute, so here we have defined the type, so it's a float f, and after that it needs a geometry node. So because we are using the first input, let's add a 0, and if you are importing this from the second input, you can add a 1. Okay, so let's change this to 0, and after that it needs an attribute name, and it is in string. So we have the attribute name, we call this one active. Okay, and after that it requires the point number from which point it will read the attribute. So in here let's add an at ptnum. Okay, for the current point number. Okay, so now let's hit play and check. And for checking, let's go into the pop solver and let's lower the min and max substeps. Let's change this to 1. And also onto the pop grain, let's lower the constraint iteration. Let's change this to 5. This is for the faster working. Okay, and let's hit play. And here, as you can see, our active attribute is activating these grains. Okay, so we have successfully imported the attributes inside of top. So let's increase the constraint iteration. Let's change this to 20. And also let's increase the min and max substeps. And onto the pop color, let's remove the attraction weight as an visualizer. And let's remove these double slashes to enable our ramp, random ramp. Okay, and in here let's select the sand preset for coloring. Okay, and onto the pop grain node, let's increase the particle separation. Let's change this to 0.02 to generate more particles. And here right now, as you can see, we have these particles in these regular grid array. So let's go back here onto the grain source node. Let's enable the jitter scale option to add an jitter. And here, as you can see, now we don't have these regular arrangement of our particles. Okay, and also we can uncheck the uniform radius to create a random scale. Okay, so now we have a random variation of 0.5. and let's go into the popnet and let's increase the particle separation. Let's change this to 0.05. Okay, and let's hit play. Okay, so before I hit play, let's disable our activation attribute. Okay, so let's bypass this pop wrangle node and let's hit play. And here, as you can see, some of our particles are exploding, and that is because here onto the pop grain we need to uncheck the assume uniform radius. Okay, because we are using the random radius for these particles. So let's uncheck this option. So now the solver will work correctly. Okay, and let's check. And here, as you can see, now we don't have the exploding simulation. Okay, and let's enable the pop wrangle again. And here, as you can see, when I enable the pop wrangle, our simulation gets dramatically slow. So let's go back, and that is because here we are cooking the grain source at every frame. Okay, so this clock option means that this node is in time dependent. Okay, so what we can do, we can disconnect the attribute wow from here, and let's use the static geometry for creating these constraints. Okay, so now we don't have the clock option, so which means now this node will only cook for one frame. Okay, and now let's go back and let's check. And here, as you can see, now we have a very fast simulation. Okay, and let's go into the pop grain and let's lower the particle separation. Let's lower this down to 0.01. Okay, so the value of 0.01 is taking too long, so let's change this to 0.015 and let's check. Okay, so here on 0.015, if we middle click, here we have almost 1 million particles. Okay, so let's go back here onto the popnet. Let's add a clean swap to remove all of the unwanted attributes. Okay, and let's connect that. And in here let's check remove attribute, remove groups, and uncheck the remove unused, and remove degenerate primitives. Okay, and here as you can see we are importing the ground plane from the top as well. So let's go into the popnet, and here we have the pop object, and that is the ground plane. So let's go into the popnet and onto the object. So here we have the wildcard, which means all of the object will be imported. So in here let's add a pop. So now we are only importing the pop object, this one. Okay, so now here as you can see, now we don't have the ground plane. So now let's check, and here as you can see now we only have the points. And onto the clean node, let's retain the ID attribute. Okay, so we will need the ID attribute for rendering. Okay, so now we do have the ID attribute, and let's add a file cache node, and in here let's write out the 120 frames. Okay, and let's write the caches out. Okay, so I have written out all the caches, and here is the result. Okay, and into the clean swap I forgot to add the p-scale attribute. Okay, so we need the p-scale attribute for the scaling of the particles. Okay, so in here let's add an exception for the ID and an p-scale. So now we have the ID and as well as the p-scale. Okay, so now let's go back, and in here let's add a grid for the ground. So in here let's add a grid node. Okay, and let's unpin this view. Okay, so here we have the grids. Let's scale the grid up. Okay, so onto the uniform scale, let's increase its uniform scale. Okay, and now let's go on to the stage context, and in here let's add a SOP import node, and let's import out our grains. So let's go into the object level, and after the file cache let's add a null, and let's call this one out grains, and let's go into the stage context, and in here let's select our out grain null. Okay, and call this one grain, and let's also add another SOP import, and in here let's import our grid. So let's go into the grid geometry, and let's select the grid, and let's call this one ground, and after that let's add an merge both of these ground and the particles, and let's add a dome light for lighting, and let's connect that. And onto the dome light let's select an HDRI skylight garage. Okay, and now let's create the materials. Let's add a material library, and let's connect that and dive inside, and in here let's create a material X standard surface, and this one let's call this one grains, and let's duplicate this material X standard surface, and let's call this one ground, and onto the ground. Let's go into the specular, and let's add the full specular roughness. Okay, and onto the grains, let's use the random ramp for setting the colors for the grain. So in here we have a material X ramp node, material X color ramp. Okay, and let's connect the random attribute into the input to generate a color ramp. Okay, so for that, let's go into the geometry level and onto these particles. Let's add an attribute wrangle node, and let's generate a random attribute. Okay, so let's call this one float at rand. Okay, so we are creating an attribute named rand, and in here let's add a rand function, and let's use our particles ID to generate the random value. Okay, so now we have a rand attribute. So let's now, in the stage context, let's import our rand attribute. So for that, let's add a UST primvar reader, and in here let's type the attribute name. So we have created an attribute name rand, and let's connect this into the ramp, and let's connect this into the base color. And onto the ramp, let's select the gear icon and select our sand preset. Okay, and let's also select the grain material, and onto the specular, let's add a specular roughness of 0.8, and let's go back and click on the autofill material to fill the material slots, and let's assign these materials. And let's remove the stage from the path. Okay, and after that, let's add a karma render node. Let's connect that, and in here let's choose the XPU render engine, and in here let's select the karma for rendering. And here, as you can see, we are rendering the sand. Okay, let's disable the lights guide as well as disable the environment light into the background, and also set this to dark and disable the grid. Okay, and let's go into the material library, and here onto the ramp we can adjust the color. So let's adjust the white particles. Okay, so onto the white particles, let's lower down the color value so they are not too bright. Okay, and let's also select the first point, and let's create a more darkish brown sand, as well as lower down the saturation, less saturated color. Okay, and let's select another frame for checking, and let's also adjust the floor color as well. So let's go into the ground material, and let's lower down its brightness value for the floor, and also so here we are adjusting the specular color. So let's go into the base color. We need to adjust the base color. Okay, so let's lower this down, and here, as you can see, now the floor color is changing. Okay, and from here let's create a camera, and let's connect the camera up here into the merge. Let's remove this point, connect it connect it there, set the display flag to the karma, and adjust the camera position. Okay, and let's go into the dome light, and let's add an exposure, and let's hide the shelf, and let's also increase the grid size as well. So let's go into the object level, and in here let's increase the uniform scale. Let's change this to 10. Okay, and now let's check. So the scale is still small, so let's go into the object level, and let's increase the uniform scale, set this to 100, and let's go back and check. Okay, now let's go into the USD render op, and let's select the render frame range. Okay, and let's render out these sequences. Okay, rendering has finished, and here we have the sand rendered. Okay, and right now our sand particles are too big, so we need to adjust the particle separation for more high-res sim. Okay, and for the grid scaling, so here if we go on to the object level, so we are scaling the grid from here onto the object level. Okay, so this scale value is not being imported into the Solaris, so let's change this to 1. So the scale to be imported, we need to scale the actual grid down. Okay, so because this is the geometry that we are importing, so in here let's add a transform node, or you can adjust the grid size from here. So let's change this to 100 by 100. Okay, and let's go back into the stage context, and here as you can see, now we have our grid in the correct scale. Okay, and for the final rendering, we may need to go back into the PopNet, and in here onto the pop grain, adjust the particle separation, so lower this value down for more high res rendered. Okay, now let's see how we can simulate soft body simulations with grains. So let's create an geometry node and dive inside, and in here let's create a tube, and let's increase the height of the tube, and let's lower down the radius and add the end caps, and let's change the center to move the tube up, and let's rotate this in an angle, and maybe let's also decrease the scale, and in here let's add a box. So this box will act as a collider, so let's change its size. Let's change the X size, and onto the Y, let's lower the Y size down, and let's increase the Z size, and also change the center to move the collider up. Okay, and now let's change the tube into grains. So let's add a grain source node, and let's connect that, and let's go into the material visualizer, and let's change this to lit sphere. Okay, and onto the grain, let's adjust the particle separation. Let's change this to 0.05 maybe. Okay, and also create the constraints. So let's create the explicit constraints, and let's increase the search radius until we have all of these grains particles connected. Okay, and now let's add a pop network, and let's connect that and dive inside the pop net, and onto the pop source node. Let's change this to all geometry, and onto the birth let's add an expression $FF for current frame is equal to 1, and let's add a pop crane, and let's connect that, and onto the pop crane let's change the explicit constraint weight to 1 to utilize these constraint geometry. Okay, and let's go into the pop source and disable the guides, and to visualize these grain particles let's go into the SOP level, and in here let's pin our viewport to the SOP, and now let's dive inside, and for collision let's add a static object, and from the static object let's select the SOP path, and let's select our box. Okay, and also let's add a ground plane, and let's merge both of these collider. Let's add a merge, and let's merge the ground plane as well as the static object, and onto the relationship, the effector relationship, let's change this to mutual. Okay, and let's add a gravity force and connect it here, and let's hit play. Okay, so here as you can see our box is not colliding correctly with the grains. So let's go into the pop solver and let's increase the substeps. So let's change the substeps to 10, min and max to 10, and let's check again. Okay, so now the simulation is slow but we have the correct result. So let's enable the real-time playback and let's check. Okay, so here we have the soft party simulation. Let's go back, and in here let's only import the pop object. So here onto the object let's add a pop. Okay, so now we are only importing these particles, and now let's see how we can use these simulation to simulate our original geometry to add the deformation. Okay, so for that we have a node called point deform. So let's add the point deform. So the point deform has 3 inputs. So the first one is the mesh to deform. So let's select our tube. So this is the mesh that we want to deform, and it needs the rest point lattice. So this is the resting points of our geometry of our particles, and the deforming point lattice, let's use the simulated particles. Okay, and let's set the display flag to point deform and let's check. Okay, so now we don't have the enough subdivision for the deformation. So let's go into the tube and let's add some columns as well as rows. Okay, and now let's check again. Okay, so here as you can see, now we are deforming our original geometry with the grains. Okay, so in here let's add a grid, and onto the grid let's change the size of our grid. So let's lower down the Z size. Okay, and also rotate the grid onto the X. Let's change this to 90 degrees, and let's change the Y center to move the grid up. And in here, let's put this grid into the grain source node. So first let's change the point separation. Let's change this to 0.1, and let's connect the grid. Okay, so the grid has no thickness. Okay, so it's a 2D plane. So for that, onto the grain source, we have the mode set to solid. So let's change this to sheet. Okay, so now we are generating these grains particles onto the grid. Okay, and now let's pin these side points. Okay, so for that, let's select the points mode and choose the selector, and let's select these side points, and onto the viewport, hit tab and add a group node to group these particles. So let's connect it here, and onto the group, let's call this group to be pin. Let's call this one pin. And to visualize this group, let's go into the display material and change the display to points. Okay, so here we have these particles in group highlighted in yellow. So let me remove this point deform wiring, and let's remove the tube as well as the box. Okay, so here onto the pin group, let's create a mass attribute and set the mass of these points to 0. Okay, so in here let's add an attribute wrangle node, and first let's initialize our mass. So let's initialize our first mass. Let's change this to 1, and let's duplicate this attribute wrangle node and connect it here. And onto the group, let's select our pin group, and for this group let's change the mass to 0. Okay, and now let's go into the popnet and let's dive inside. So here we have an error for static object, so let's remove that, and also remove the ground plane, we don't need that. And now let's check. Okay, so let's go into the pop solver and let's lower down the min and max substeps for faster playback, and let's check. Okay, and in here let's add a wind by creating a pop force node, because grain is a particle simulation, which means you can use these particle forces. So let's connect the pop force node, and let's give the force in the X. Let's change this to 10, and also introduce the noise. Let's change the amplitude to 5, and let's check. And let's go back in here, and onto the visualization, let's change this back to lit sphere. Okay, so here as you can see we have this flag simulation. Okay, and now let's deform our original grid. Okay, so here onto the point deform, let's select the mesh to deform, and this is our rest point lattice, and this is the animated points. And let's set the display flag to point deform, and let's check. And here as you can see we don't have enough geometry, so let's add a remesh node in here, and let's connect it there. So the remesh node will generate this triangular mesh. Okay, and let's check. Set the display flag to the pontiform and let's check. Okay, let's increase the iterations as well as adjust the smoothing. Let's increase the iteration more for a better triangulated mesh. Okay, and let's check. And here we have the soft body simulation with grains. Okay, now let's talk about rigid body dynamics. So let's create a geometry node and dive inside, and in here let's add a test geometry pig head. Okay, and here as you can see, onto the pig head geometry we have 2000 points and 2000 primitives. Okay, and if we were to simulate all of these points, it will be slow and not very efficient. So what we can do, we can add a pack node, and let's pack our geometry. So when we add a pack node, the pack node packs our geometry onto a single point. So now we have a one pack geo. So what the pack node will does, it create a single point and it stores the some attributes. So it has the transformation matrix of the object, so it knows that where the object is in the 3D space, and Houdini knows how to draw the object. So if we go into the geometry spreadsheet and onto the primitive attribute, and in here we have some intrinsic attributes. Okay, so here we have the packed full transform. Okay, so this is the transform matrix. Okay, so it's when we pack our geometry, Houdini will create all of these attributes. Okay, so if you open the help of the pack node, and here we have the detailed information about the pack primitives. Okay, so I encourage you to check out this document to learn more about the packed primitives. Okay, so in here let's duplicate this pig head geometry, but first let's translate this up, and now let's duplicate this again, and let's duplicate this one more time, and let's add an merge node, and let's merge all of these our three pig head geometry, and let's move this one up, set the display flag to the merge, and let's move this one up a bit further. Okay, so now when we pack our geometry, and here as you can see we have still one packed geometry, so when we merge these geometries, Houdini thinks that all of these threes are in a one single object. Okay, so in here at the pack primitive we have the option to use the name attribute. Okay, to pack our object individually. So right now it's throwing an error because currently we don't have any name attribute. So let's create a name attribute in here. So let's add an attribute wrangle node, and let's connect it here, and in here let's create a name. So it's a string, so which means S for string, and create an attribute name, and let's name this one piece. Let's call this one piece 0. Okay, and let's duplicate this in here, and connect it here as well. And for this one, let's call this one piece 1, and this one, let's call this piece 2. Okay, and now let's set the display flag to the pack. So it is still throwing an error, so that is because it is expecting a primitive attribute. So right now we are creating the point attribute. So let's change this to primitive, and let's change this one to primitive as well, and this one to primitive as well. Okay, so now the error is gone. And now if I middle click here, as you can see, now we have these 3 packed fragments. Okay, so to set up the rigid body simulation, let's create a DOP network, and let's connect this into the first input, and let's dive inside the DOP net. And in here, let's create a rigid body solver, and let's connect it. And the rigid body solver requires a rigid body object. So in here, let's add an RBD packed object because we are using the packed geometry. So let's connect it here and onto the RBD packed object. So the geometry source is set to SOP, which means you can select the SOP path, or we can change this to the first context geometry. Okay, and in here, let's add a ground plane for the collision, and let's merge this ground plane in here. Let's connect it there, and let's select the relationship to mutual, and let's add a gravity force, and let's connect it there, and let's hit play. And here we have the very basic rigid body simulation. Okay, and here, as you can see, it is very fast. So that's how you can set up the basic rigid body simulation. And if we go back, and in here, the name attribute is essential for packing the geometry, because in here the pack node is using the name attribute to recognize these separate pieces of model. So if one of these objects have same name attribute, so for example, if I set these two first one to same name, okay, so let's change this one to piece 0 as well. Okay, and now if I middle click, now we have 2 packed geometries. Okay, and let's see with our RBD simulation. And here, as you can see, now we have these 2 pig heads connected, because now Houdini thinks that these 2 are a single piece of object. Okay, and you can also create the packed geometry with an assemble SOP. So if I add an assemble node, and let's connect it there, so onto the assemble node will create the name attribute, and you can check the create packed primitive to create the packed primitives. Okay, and so now we don't need this packed node, and also we don't need to create these name attribute on our own. Okay, and the assemble SOP will generate the 3 packed fragments. Okay, so it has a connectivity node inside it, so it looks for the connectivity of the object and recognize the separate pieces of geometry. So now if I simulate, here as you can see, we have these 3 objects, and for simulating these RBD, we have a RBD solver right in the SOP level. So if I right click and type the RBD solver, here we have the RBD bullet solver. So let's connect that, and let's connect this into the required geometry and set the display flag to the RBD bullet solver. So run onto the RBD bullet solver, we have some options. So here we have the time scale, And also onto the properties, we can adjust the physical properties of our geometry. And onto the collision, here we have the option to add the ground plane. So let's add a ground plane. Okay, and if I hit play, and here as you can see, now we have a RBD bullet solver set up and ready to go. Okay, and you can also adjust these physical properties of your object by RBD configure node. So if I connect that here onto the RBD configure node, you can adjust the attributes. For example, you can physical properties, you can set if this object is a concrete or glass or wood. So now Houdini will use these physical attributes to better simulate the wood material. Okay, so let's hit play. Okay, so that's the basics of rigid body simulations. Okay, now let's take a look at different geometry fracturing techniques. So let's create a geometry node and dive inside, and in here let's add a sphere. Okay, and now let's fracture our sphere into little pieces. So for that we have a node called Voronoi fracture. Okay, so the Voronoi fracture has two inputs, so it needs the geometry to fracture and it needs the points for the fracturing. So for that let's add a scatter node and let's scatter some points onto our geometry. Okay, and let's connect this into the points and let's set the display flag to the Voronoi fracture. And here as you can see, now our geometry has been fractured. So we can visualize this by adding an exploded view. So let's connect that. Let's connect this into the exploded view. Okay, and here as you can see, we have these little pieces. So onto the exploded view we can adjust the scaling. Okay, and right now we don't have these fracture pieces on the inside. Okay, and that is because we are scattering the points onto the surface of our geometry. So to add points inside, let's first convert this sphere into volume. So let's add an ISO offset and let's connect that, and the ISO offset will convert our model into volumes. Okay, let's increase the uniform sampling to 50, and here as you can see we have this fog volume. So now if I set the display flag onto the scatter, and now we are scattering points inside of our sphere as well. Okay, so now if I set the display flag to Voronoi fracture and view it with the exploded view, and now here as you can see we have pieces on the inside of our geometry as well. So let's go into the scatter sub and let's reduce the number of points. So these points will define the fracture pieces. Okay, so here we have the 44, and right now here as you can see the inside pieces are flat, so they don't have any detail. So to add the detail onto the inside pieces, we have a node called RBD interior detail node. So let's connect that, and onto the RBD interior detail, first we have the detail size. So this will control the subdivision of the inside pieces. Okay, so let's lower this down to 0.01 to add more divisions. Okay, and here we have these normal for the interior pieces. Okay, you can adjust the normal angle, and here we have the noise. Let's increase the amplitude. Okay, and let's visualize this noise by clicking on this visualize noise scale. Okay, and in here we can adjust the noise depth. Okay, and here we have the noise type. Right now it's set to sparse convolution. We can change this to a fast noise or a simplex noise. Let's change this to fast noise. Okay, and here we can adjust the frequency, and we can adjust the noise amplitude, and here we have the depth from where we want the interior noise to start. Okay, and now here, as you can see, we have some detail onto the inside pieces of our geometry as well. Okay, so let's go into the RPD interior detail and let's uncheck the visualizer. Okay, so now let's simulate our rock. So let's remove the exploded view, and in here let's add an RPD configure node, and let's connect that. And RPD configure node will use the name attribute. Okay, so when we created the Voronoi fracture node, and if I middle click onto this output, here as you can see, the Voronoi fracture node is creating the name attribute, and it has a 44 unique name. So because we are generating the 44 points, so we have 44 pieces. Okay, and the RBD configure node will using the name attribute to pack our geometry. Okay, so here as you can see, we don't have the packed geometry after the RBD configure node. Now we have the 44 packed fragments, and let's add an RPD bullet solver, and let's connect that. And onto the RPD bullet solver, let's go into the collision, and let's add a ground plane, and let's move the ground plane down. So let's change the Y position. Okay, and let's hit play. Okay, so here as you can see, we are simulating our geometry with all of these detail. Okay, and our sim is slow because we are simulating these high-res pieces. So here onto the RBD interior detail, we have a proxy geometry output. Okay, so if I add a null into the proxy geometry output, let's set the display flag to null, and after that let's create an exploded view, and let's view it with the exploded view. And here as you can see, now we have these basic pieces without all of the interior detail. Okay, so now let's connect this into our proxy geometry. Here onto the RPD configure node, we have the proxy geometry pin, so let's connect that. And after that, here we have the proxy geometry out pin from the RPD configure, and onto the RPD bullet solver, this third pin is the proxy geometry, so let's connect that. And now let's set the display flag to the bullet solver, and let's check. And here as you can see, our solver is now using these proxy geometry for simulation. Okay, and if I view the proxy geometry, if I create a null at the out, okay, So here is the geometry that we are actually simulating. Okay, and the RBD bullet solver will use these transform to transform our high-res geometry. Okay, so now let's take a look at the different geometry fraction techniques. Okay, so in here let's create a box, and let's set the display flag to the box node, and let's create a piece of wood. Okay, so let's scale this down and also scale the Y size up, and let's scale the Z size down as well. Okay, so let's scale it even more down to create a thinner wood plank. Okay, so now to create a wood like fracture pieces, what we can do, we can add a transform node in here, and onto the transform node let's scale down the Y size. Okay, and in here onto the transform node, if you right click and go into the actions and create a reference copy of our geometry of our transform node. Okay, so this reference means that all of its parameters are referenced to this transform node. So if I change any option from here, this transform node will reflect those changes. Okay, so let's zero out the rotation and let's connect it here. So here onto the reference copy, what we can do, we can remove this invert transformation channel. So right click and say delete channel and click on the invert transform node to reverse all of these changes that we have made onto the transform node. Okay, so basically we are restoring the original scale of our box. Okay, so what we can do, when we have scaled down the box, we can scatter some points. So let's add a scatter node and let's connect that, and in here let's lower down the force total count, and let's add a Voronoi fracture tool, and let's connect this geometry, and these are the points. Okay, so here we are fracturing these points, and after the transform node we are scaling those pieces back up. Okay, and now if I add an exploded view and connect that into the exploded view, and here as you can see, let's lower down these force total count. Okay, and we have these wood like structure. Okay, so to create these more lengthier wood patterns, we can scale the original box even more down. So let's scale it more. Okay, and here as you can see, as I am scaling the down, I'm making these pieces more and more length in height. I'm increasing the height of these pieces. Okay, so in here onto the scatter, let's add more points. Okay, and onto the exploded view we can check. Okay, so that's the basic wood fracture, and in here we also have a node RBD material fracture. So let's add that. So let's connect our box into the RBD material fracture, and onto the RBD material fracture we have the option to set the material type. So right now the material type is set to concrete. Okay, so now it is fracturing the geometry considering that it's a concrete piece. Okay, we can change this to glass, and now we have a glass like shatter, or we can change this to wood. Okay, so here we have a very accurate wood fracturing pattern. So if I add the exploded view here, and let's connect that into the exploded view, and here as you can see it is generating these wood fracture like splinters. Okay, so here onto the RBD material fracture we have the option to enable these grains. Okay, so also we have the option to enable the cuts. Okay, and we can also visualize these guide geometry. So if I visualize the grains, and we need to set the display flag onto the RBD material node to visualize. Okay, so here we have these grains. So these are the planes that are cutting our wood in the y-axis. Okay, so if I go into the grain, I can adjust the grain spacing to create more or less vertical pieces. Okay, and here we have the noise. Here I can adjust the noise amplitude, and here we have the element size of the noise, and I can also visualize these cuts. And if I go into the cuts, so here we have these cuts in along the height. Here we can adjust some parameters. We can adjust the skews as well as cut spacing. Okay, and also we can add the detail. So right now onto the detail we have the detriangulation option set to all polygons. Okay, so if I change this to no polygons, so here as you can see we have a triangulated mesh. So let's keep this to all polygons to avoid these unwanted triangles. Okay, and also let's change the material back to concrete, and here onto the concrete we have a primary fracture, and onto the primary we have two level of fractures. So that's the one level and that's the second level. Okay, so onto the first level, here we can adjust the scatter points to create more of these fracture points. So let's increase this to 20. Okay, and onto the second, let's increase this to 40. Okay, and here as you can see now we are generating a lot more pieces. And also we can go into the chipping and add a chipping. Okay, so what the chipping wheel does, it adds these small fracture pieces around the corners. So here as you can see we have these small pieces around the corners. So if I disable the chipping, and here as you can see now we don't have these small pieces. Okay, so let's go back onto the box, and maybe let's in here let's create another box, and let's connect this into the RBD material fracture. Okay, so we have this default box, and let's see with the RBD material fracture node, and let's view this with the exploded view. Okay, so let's go into the RBD material fracture, and onto the detail we can enable the edge detail. So if I increase the exploded view scale, and here as you can see the inside pieces has no detail. So if you enable the edge detail or the interior detail, so these two are separate things. So the interior detail is an RBD interior detail sub. Okay, so this is the node that is actually connected inside, and if we enable that, and here as you can see we are adding the interior detail, and if I enable the edge detail, so this will add the detail around the edges. So if I turn the exploded view scale down, and here as you can see now we have these edges distorted. Okay, so if I disable the edge detail, and here as you can see now we have these straight lines. So let's enable that, and in here we can adjust the noise height. So let's increase the height to make more pronounced edges. Okay, and make sure not to increase too much of height. Or here as you can see we have some intersection geometry, and it is removing these pieces that are intersecting. Okay, so let's lower this down to 0.2 maybe. Okay, so you can't go crazy with the noise height. Okay, so that's the RBD material fracture node. Okay, now let's take a look at the fracture pieces clustering techniques. Okay, so let's create a geometry node and dive inside, and in here let's add a box, and let's add an ISO offset to convert this into volume, and let's increase the uniform sampling. Let's add a scatter node to scatter the points, and let's add a Voronoi fracture, and let's connect the box into the geometry, and these are the points, and here we have the standard Voronoi fracture. Okay, so in here we have a node called RBD cluster node. Okay, so let's connect that, and here onto the RBD cluster node let's click on this visualizer to visualize these cluster. Okay, so here we have these multiple fracture pieces connected together, visualize in color. So if I add an exploded view and connect that into the exploded view, and here as you can see we have these chunks, connected chunks. Okay, so here onto the RBD cluster view we have the option to randomly detach some of these pieces. Okay, and we can disable that, and here as you can see we have these three pieces, big pieces. So here onto the size we can adjust the size of these pieces. Okay, so let's lower that down to create these more connected pieces. So what the RBD cluster sub is doing, it's creating the same attribute for multiple pieces. Okay, so by using the RBD cluster node you can generate these piece variation to break the basic Voronoi fracture shape. Okay, so after that let's add an RBD interior detail sub to add the detail into the interior pieces. So let's connect that, and let's lower the detail size to 0.01. Okay, not 0.1, 0.01. Okay, so here as you can see we now have this division inside of these pieces. So let's go into the RPD cluster sub and click on this visualizer to disable the visualization. Okay, so that's how you can cluster multiple pieces together. Okay, now let's take a look at the Boolean fracture node to fracture our geometry. So let's create a geometry node and dive inside, and in here let's add a box, and let's convert this box into volume by adding an ISO offset, and let's connect that. And here onto the ISO offset, let's increase the uniform divisions, and let's add a scatter to scatter the points, and onto the scatter sub let's lower the number of points. Okay, and after that let's add a grid, and let's copy our grid into our scattered points. So let's add a copy to points node. Let's connect the grid into these points. Okay, so now the grid is on top of each other. So let's randomize the orientation of the grid. So into the scatter let's add an attribute randomize node, and let's connect that. And here onto the attribute randomize, let's randomize the normals. So let's add an n. So we are randomizing the point normal. Okay, so now if I set the display flag onto the copy to point sub, so let's go into the randomize and onto the distribution. Let's change this to inside sphere. Okay, so here we have these cutting planes randomly oriented. Okay, so if I set the display flag onto the box, and if I template my cutting planes, and here as you can see all of these planes are going through this box. So maybe let's decrease the grid size. So right now the size is too big. Okay, so let's set the scale to 3 by 3, and after that let's add a Boolean fracture node. So let's connect that. So it has two inputs, the geometry to fracture and the cutting surfaces. So let's connect that. And if I set the display flag to Boolean fracture, and here as you can see our geometry has been fractured with these cutting planes. So let's add an exploded view to view our fracture pieces, and let's connect that. And here as you can see we have our fracture geometry. So let's go into the scatter sub and let's lower the number of cutting planes. Okay, so here because we are using these planes to cut our box, so we can add the noise into these planes, so that way we have the interior detail into our pieces. Okay, so onto the grid let's add a mountain node, and let's connect that. And here onto the grid let's increase the rows and columns to add more detail into our cutting plane. Okay, and let's go into the mountain sub and let's adjust the amplitude as well as the element size. And if I set the display flag to the copy to points, so here we have these noised up cutting planes. So let's view this with our Boolean fracture node, and here as you can see now we have these interior detail added. Okay, so now they are not straight pieces like the Voronoi fracture. Okay, so that's the Boolean fracture node. Now let's see how we can activate our rigid body simulation with the attribute. So let's create a geometry node and dive inside, and in here let's add a file node, and let's select our marble bust geometry. Okay, and as always let's add a clean node to remove all of these attributes. So let's remove the attributes and remove the groups, and after that let's add a match size. Match size node, and let's check scale to fit, and let's change the size to 3 by 3, and onto the justify y let's change this to minimum. And now let's add an ISO offset, and into the ISO offset let's increase the uniform sampling, and let's add a scatter node to scatter the points, and let's move this into the side, and let's add a Voronoi fracture node to fracture our geometry. So let's connect that and connect this. Okay, so Voronoi fracture is fracturing our geometry. Okay, so here we have the fracture geometry. So now let's create the activation attribute. Okay, so for that let's add a distance along geometry node, and let's connect that, and onto the distance along geometry node let's select the start point, and let's select the point where we want the activation to start. So let's select this point and press enter. Okay, and now let's add an attribute warp node, and let's dive inside the attribute warp node, and in here let's bind import our dist attribute. So the attribute name is dist, and after that let's add an add node for the offset, and a parameter node, and onto the parameter let's rename this to offset, and after that let's add a fit range, and let's connect this into the fit range, and the ramp parameter, let's connect the fit range to the ramp parameter, and now let's connect this into the CD, and let's go back. First let's go into the ramp, and let's choose the ramp type to spline ramp, and let's go back, and onto the ramp let's select the first point and give him a value of 1, and in here let's animate our offset value. So let's increase the offset until we have no value. So let's add a key, and let's go into the frame 100, and let's change the offset. Okay, and let's add a key. So now we have the fading gradient. So now let's dive inside, and onto the fit range let's adjust the source max to adjust the gradient. Okay, so now let's write this attribute out. Let's add a bind export node, and let's connect that into the ramp parameter, and let's call this attribute active. Okay, and now let's go back, and now let's transfer the active attribute onto these our fracture geometry. So let's add an attribute transfer node, and let's select this one is the geometry and this one is the geometry from attribute. So here onto the attribute transfer, let's uncheck the primitive and let's specify only the active attribute. Okay, and after that let's add RBD configure node to create an pack geometry. Okay, so now we have the pack geometry. RBD configure node is packing our geometry. Okay, and now we are transferring the active attribute onto our pack geometry. So now let's add an RBD bullet solver and let's connect this into our geometry. And now let's set the display flag to the RBD bullet solver and hit play. And here, as you can see, our active attribute is not being imported at every frame. So to import the animated attribute, so we need to dive inside the bullet solver. Okay, so now we are in the DOPS, and here, as you can see, we say we can enwire pop forces to resolve the per point forces. Okay, so in here let's add a pop wrangle node to import our active attribute at every frame. Okay, so here onto the pop wrangle, first let's go into the input, add onto the input 1, let's set this to SOP. Okay, and now let's go back, and after the active let's create a null, and in here let's call this one out active, and let's dive inside the bullet solver and let's select our out null. Here we have the out active null, so hit accept. Let's go into the code, and in here we have the attribute name active. Okay, so the active attribute is the attribute that bullet solver understand, so it is an integer attribute. So first type I for integer and the attribute name is active. Now let's use our point function to import the attribute. So the geometry is the 0 and the attribute name is the active, and for the point number let's use the current point number as a point number. Okay, add ptnum. Now let's close this bracket and add a semicolon, and now let's go back and let's go into the first frame and let's hit play. And here, as you can see, now we have the crumbling geometry effect. Okay, and because we are referencing this out null inside of the pop wrangle, so which means we don't really have to connect this animated geometry into the geometry input slot of the RBD bullet solver, so we can use this RBD configure static geometry. Okay, and if we hit play, our attribute will still work. Okay, so that's how you can activate your RBD pieces. Okay, now let's talk about constraints. So let's create a geometry node and dive inside, and in here let's add a sphere, and let's add a copy transform node to copy the sphere. So in here let's change the translation X. Okay, and here we can increase the number of copies. And now let's here onto the sphere node, let's change the center and move the sphere up. Okay, and now let's create an assemble node to create the name attribute and as well as pack geometry. So let's connect that, and here onto the assemble node, let's check the create pack primitive, and to create the constraints between them, we have a node called RBD constraint from rules. So let's add that node and connect that, and here onto the RBD constraint from rules, let's increase the search radius. Okay, so here as you can see, the color of our sphere has been changes, indicated that these now are connected together with constraint. So we can visualize the constraint. So let's add a null. Center output is the constraint output, so let's connect that into the null and set the display flag to the null. And here we have the constraint, so it is a straight line that is connecting all of our geometry pieces. Okay, and it has the points, so its number of points is equal to the number of geometry pieces. Okay, and here on to these points we have some attributes. So we have the name attribute. Okay, so if we go into the geometry spreadsheet, and here we have the name attribute. So piece the point 1, we have the P0, and P0 is connected to the point number 1 of our line geometry. Okay, onto these points we have the connectivity information. Okay, so after that let's add an RBD constraint properties node, and let's connect this is the geometry and these are the constraint. And here onto the RBD constraint property node, we can set the constraint type. So if we want to create the constraint type glue or hard or the soft constraint, so let's change this to glue. And now let's add an RBD bullet solver, and let's connect that, and let's connect the constraint geometry. Okay, and in here let's go into the collision and add the ground plane, and let's adjust the Y position of the ground plane, and let's hit play. And here as you can see, all of our sphere are now connected together. Okay, with the glue constraint. So here we have the set the glue constraint. Okay, so we can change this to soft constraint. Okay, and to visualize the soft constraint, let's add a collider in between. So let's create a box, and let's connect this into the collision input of our geometry. Let's adjust the box size, and let's scale the Y size down. Okay, and also let's onto the sphere, let's change the center. Okay, and now let's check. Here as you can see, we have these soft constraint relationship between them. Okay, so in here let's create another box. Let's set the display flag to the box node, and onto the box let's adjust its X size, and let's lower down its Y scale, and let's change the center to move the box up. Okay, and let's add a transform node in here, And now let's rotate this around the y-axis. Let's change the rotation to 90 degrees and let's adjust the position and bring it down. Okay, and here let's template this. So here we have the box, so this will act as a collider. Okay, so and now let's fracture this box. So let's add an ISO offset for converting the box into volume, and let's increase the uniform sampling. Let's add a scatter node to scatter the points. Okay, and let's add a Voronoi fracture node and connect the geometry to geometry, and these are the points. So here we have the fractured box, and Voronoi fracture will generate the constraints. Okay, so if I connect the null into the constraint output, and here as you can see we have these constraints. Okay, so now let's use the RBD constraint property in here, and let's connect this into the constraint output and onto the RBD constraint. So the constraint type is set to soft. So let's delete this box, we don't need that. And now let's connect. So right now our geometry is not packed, so let's add an RBD configure node to create the packed geometry. So let's connect this into the geometry, and these are the constraints. Okay, so now RBD configure will creating the packed geometry, and let's connect this into these ports, and here we have the collider. So let's connect this into the collision input, and let's set the display flag to the bullet solver, and let's check the result. Okay, so here as you can see we have these glue constraint, and onto the RBD constraint properties we can change this to, right now we have the soft constraint. Okay, so here we have the soft constraint behavior. Let's change this to glue constraint. Okay, and now let's check, and here as you can see these pieces are now glued together, and when they hit the collider the glue constraint is breaking. So here we can adjust the strength of the glue constraint. So let's lower down the strength and let's check, and here as you can see now more of these pieces are breaking. So let's lower the strength again and let's check, and let's keep decreasing these glue strength. Okay, and maybe let's change this to 100, and let's go back and check. Okay, so here as you can see now we have a very weak strength of the glue constraint. Okay, so let's change this to soft constraint and let's check. Okay, here we have the soft constraint behavior. So if you go into the plasticity, we can enable the plasticity. So now if I hit play, so here onto the plasticity we can adjust the plasticity rate. Okay, so if you increase the plasticity rate, so now our geometry will keep the deformation. Okay, and let's also increase the hardening and let's lower down the rate and let's check. And here as you can see now we have this springy behavior because now the constraints are hard. Okay, so we can create the soft body effect with these soft constraints. So here we have the original box geometry. Okay, so let's remove this setup, we don't need that. So here onto the original box, so let's add a point deform node, and let's connect the box into the mesh to deform, and here it needs the rest point lattice. So let's connect this. This is our rest point lattice, and this is our animated points. And let's set the display flag to the point deform, and to add the deformation correctly we need to add the divisions. So let's add a divide node, and let's connect that. And here onto the divide node, let's uncheck the convex polygon, and let's check the breaker polygon option, and here let's decrease the size to add more divisions. Okay, so now let's hit play, and here as you can see we are deforming our original geometry, and here as you can see we have these jagged edges. So let's go into the point deform node, and in here let's increase the radius to smooth out these points. Okay, so now we have a very smooth deformation of our geometry. So let's go back onto the RBD constraint, let's lower down the hardness, and let's check. Okay, so that's how you can set up these constraints. Okay, now let's talk about the vellum solver. So the vellum is used to create the soft body simulation. So let's see how we can set this up. So let's create a geometry node and dive inside, and in here let's add a grid, and onto the grid let's change the scale, and let's scale down the grid, and let's move the grid up, and let's add a sphere node for the collision. Okay, so here we have the sphere, and if I template my grid, so here as you can see we have some space. Okay, so here onto the grid let's add a vellum constraint node. So let's click that, and let's add and connect this into the first input of vellum constraint. So here onto the vellum constraint we have the constraint type. So right now the constraint type is set to the distance along edges. So here we can choose the different constraint types. So here we have the cloth constraint to create the cloth. Okay, so let's change this to cloth, and here the vellum constraint will generate these constraint geometry. Okay, so the middle pin is the constraints. So if I add a null in here, and let's connect the middle pin into the null, and here we have these constraints. Okay, and we are going to simulate these constraints over time. So let's set the display flag onto the vellum constraint, and here we can set some properties of these constraints. So for example here we have the option for the stretch, and here we have the stretch stiffness. Okay, so that's how much the constraint resists the stretchiness, and down here we have the bend, and that's the bend stiffness. So that's how much these constraint resist the bending. Okay, so after that let's add a dop net, DOP network, and let's connect this into the first input and connect the constraint geometry into the second input of our DOP net. And let's dive inside, and in here let's add a vellum solver node, and let's connect that. And in here let's add a vellum object, so let's add a vellum object node, and let's connect that. And here onto the vellum object, so we can set the initial geometry, okay, or we can create a vellum source node. Let's connect the vellum source node, and let's connect this into the post solve. And here onto the vellum source we can set the solve path, so let's go back, and in here let's onto this one, let's call this one constraints, and let's duplicate this null and connect it here, and let's call this one the geo, and let's dive inside and onto the vellum source. So here onto the solve path let's select our geo null, and onto the constraint solve path let's select our constraint null, okay. And for the collision let's import our sphere, so let's add a static object, and let's merge this into our scene, and let's connect this and set the relationship to mutual. And onto the static object let's select our sphere, okay. So here we have the sphere, so now we have the collider, and let's also create a gravity force. Let's add a gravity force and connect that, and now let's hit play. And here as you can see we have a very basic vellum simulation. So let's go back and let's add more divisions to our cloth. So let's add a remesh node, and let's connect that. And now let's view the result here onto the DOP net, and let's check, okay. So that's the very basic vellum cloth simulation. And after that let's add a vellum post process node, and let's connect this into the geometry. And here onto the vellum post process we have the option to subdivide, so here onto the subdivision let's change this to loop, because we are using these triangulated mesh, so the subdivision loop work best with the triangulated mesh. And now here as you can see we have a very smooth cloth, okay. And if we dive inside the DOP net, here onto the vellum source node, so right now we are importing our cloth at the first frame, okay. So if you want the continuous emission of the cloth, you can change the emission type to each frame or each substeps, okay. So if I change this to each frame and hit play, now here as you can see we are emitting the vellum geometry at every frame, okay. So let's go into the activation, let's add an expression in here, and let's skip every turn frame, okay. So for that let's add an expression $FF, and let's add an $F mod 10, okay. So if our $n f mod 10 is equal to 1, okay, so which is true for every 10 frame, so we are basically skipping the 10 frame, okay. So if I hit play, and here as you can see we are stacking the cloth, okay. So let's go back, and in here we are emitting the grid. So maybe let's change our shape in here. So in here let's add a sphere, and let's connect this into the remesh node and onto this sphere. So that is our collider sphere. So let's remove this, we don't need that. And for collision, let's create a box, and let's template our box geometry, and let's increase the X size, let's increase the Z size as well as the Y size, and let's add an X offset and move the collider up a bit, okay. And here onto the sphere, let's adjust the center and also move him up, and after that let's give him an upward velocity. So let's add a point velocity node and connect it after the remesh, and here onto the point velocity let's change this to set to value, and let's give him a value in the Y and as well as in the negative x-axis as well. So if we enable our velocity vectors, here as you can see we have these velocity vectors, okay. So let's disable the velocity visualization, and let's click on the DOP.NET, and into the DOP.NET let's import this box as a collider. So let's go into the static object, and let's select our box as a collider, and let's also add a ground plane into the collision as well. So let's connect this and onto the merge. So we have the effector relationship set to mutual, which is correct, and let's hit play. So velocity is very weak, so let's go back here onto the point velocity. So let's scale this velocity, so let's change this to negative 10 by 10, okay, and let's check. So now we have a very high velocity, okay. And also let's add a curl noise into this velocity, okay. So now we have the random velocities for our vellum objects, okay. So that's how you can continuously emit your vellum geometry, okay. And in the SOP level we have a vellum solver. So let's connect that. So here we have the vellum solver. So here we have the vellum geometry. So let's connect that, and it has the constraint geometry. So let's connect that, and this one is for the collision geometry. So let's select this box for as a collider. So let's connect this into the collision input. Let's set the display flag to the vellum solver, okay. And here onto the vellum solver, we have the option to set the time scale as well as the constraint iterations. And onto the collision, let's enable the ground plane. Okay, and let's hit play. Here, as you can see, we have the basic vellum simulation. Okay, so that's how you can set up the vellum simulation. Okay, now let's take a look at the different vellum constraint types for creating the soft body simulation. So let's create an geometry node and dive inside, and in here let's add an grid. Okay, for creating an cloth, so let's scale down the grid. Okay, and vellum simulation work best with the triangulated mesh, so let's add a remesh node to convert our geometry into the triangles. So let's connect that, and here, as you can see, we have these triangulated mesh. So let's pin these side point. Okay, so I want the side points to be pinned down, so when we add the gravity, I don't want the cloth to fall down. Okay, so we can change the selection to points and select these side groups. Okay, or in here, for creating the cloth, pieces of cloth, we have a node called planar patch node. So let's set the display flag to the planar patch, and here, as you can see, we have a simple grid with the triangulated mesh. And here onto the planar patch node, we can adjust the build plane, so we can set the orientation. Okay, and here we can set the edge length for the triangles. Okay, and also we have the dimension. We can change the shape, so right now it is a rectangle, or we can change this to trapezoid, so now it has the option to taper as well as add an skew. Okay, or we can change this to circle to create a circular piece of cloth, and also we can change this to ring. So here we have the arc. Okay, so let's change this to rectangle, and onto the seams we have some option to output the groups. So here we have the option to output the left seam group. Okay, so now these left points will be in the groups. Okay, so if I middle click, here, as you can see, I have a point group named planar patch left. Okay, and also we can add the group on either side of the patch. So let's enable the top seam group. Okay, so now these top points will be in the group, and also we can specify the top points as well. So if I enable the point, and here, as you can see, if you manually want to set these top points, okay, you can do that. So let's disable this, and now let's create a vellum configure cloth. So let's add this constraint, and let's connect this into the geometry, and after that let's select the node and type the vellum solver. Okay, so when the node is selected, press shift enter. So now it will connect all of these ports into the vellum solver. Okay, so here onto the vellum cloth node, so here we have the option where it says pin to animation. So let's select our top group to pin these points. Okay, and let's bring up the play bar and enable the real-time playback and hit play. And now here, as you can see, our cloth has been pinned into these top points. Okay, So now let's add a wind. So let's dive inside the Vellum solver. So now we are in the DOPS. So in here we can add the forces. So let's add a pop force node, and let's connect the pop force into the forces, and here onto the pop force let's give a force in the Z direction. So let's change this to 5, and let's also add the noise in the wind. So let's change the amplitude to 2, and let's see the simulation result. Okay, let's disable the point display. Okay, and let's also maybe increase the noise amplitude a bit more. And here, as you can see, we have the cloth in the wind. Okay, so let's also increase the swirl size to add more wrinkles and folds into the cloth. Okay, and let's go back here onto the Vellum cloth solver. So here we have the stretch stiffness. So if I lower down the stretch stiffness, and here as you can see our cloth is stretching. So let's lower this down to 0.01 and let's check, and it's stretching too much. So let's change this to 1 maybe, and let's check. Okay, so clearly you can see the cloth is stretching. Okay, so that's the Vellum cloth, and let's create a solid soft body simulation. So let's add a truss geometry rubber toy, and let's connect that. And here we have our rubber toy geometry. Let's go into the rubber toy, and let's increase the translation in the Y. Let's increase it even more, and after that let's add a Vellum configure tetrahedral soft body. Okay, so let's add that. So when you add the tetrahedral soft body, it creates the node called TET_conform. So if I connect this into the TET_conform node, okay, and let's set the display flag to the TET_conform, and here as you can see now our mesh is converted into tetrahedron. And if I middle click, here as you can see we have the tetrahedrons. Okay, and what the tetrahedrons are, if I add a clip node in here, let's add a clip. So let's connect this geometry into the clip. So the clip node will clip the geometry along in a plane. Okay, so right now the direction is set to Y, and if I increase the distance, here as you can see we are clipping the geometry. So in here let's change this to Z. Okay, let's change the direction Y to 0 and Z to 1, and here let's adjust the distance. And here as you can see we have a hollow mesh. Okay, so that's the polygonal mesh that is hollow inside. So if I connect the clip node into the TET_conform node, and here as you can see now we have the mesh all filled up. So let's add a normal to create the inside normal. Okay, so let's add a normal node, and here as you can see now our object is a solid, so it is filled with these tetrahedrons. So after the rubber toy, let's add a remesh node. So this node works best with the triangulated mesh. So let's add a remesh node, and also onto the rubber toy let's not add the shader, and let's set the display flag to remesh. And onto the remesh let's lower down the target size. Let's change this to 0.07 maybe. Okay, and also So add shader is checked off. Let's uncheck the UV visualization. Okay, and now let's set the display flag onto the clip, and here as you can see we have this geometry filled. Okay, so here Houdini will create the vellum constraint for the tetrahedral mesh. Okay, so after that let's add a vellum solver node. Let's connect that by pressing the shift enter, and onto the vellum solver let's enable the ground plane, and also let's adjust the ground plane position, and let's hit play. And here as you can see we have a soft body that is actually solid inside. Okay, so let's go into the vellum constraint node, and in here we have the stretch stiffness. So right now the stretch stiffness is very low. Okay, so let's change its multiplier. Let's change this to a higher value, and let's check. And now here as you can see we have a very stiff soft body. Okay, so in here let's add a collider, maybe a sphere. So let's remove this one, and let's add a sphere in here, and onto the sphere let's change this to polygons and increase the frequency. Okay, so this will create the nice triangulated sphere. And let's also move the sphere, and after that let's add a vellum constraint node, vellum constraint, and let's connect that. And here onto the vellum constraint let's change the constraint type to shape match. Okay, so the shape match constraint is like a rigid constraint. Okay, so now our object won't deform like a soft body, but it will keep its original shape. So to add this one into the simulation, so let's merge both of these geometries and constraints. So in here let's add a merge node, and let's select both of these geometries output. Okay, so here we have the geometry, and let's call this one geo. And now let's merge both of these constraints. So let's add another merge in here, and let's select this constraint and as well his constraint, and let's call this one constraint. Okay, and now let's put this into the geometry slot, and this is the constraint. So let's connect the constraint geometry, and also let's go into the sphere and let's move the sphere up a bit more. Okay, and now let's set the display flag to vellum solver, and let's check. Okay, so now here as you can see we have this soft body and we have this rigid collider. Okay, and let's go into the sphere and let's add a point velocity into the downward direction. Let's add a point velocity node, and let's connect that. And onto the initialization let's set this to value. Let's give him a negative velocity of 13 maybe, and let's check. Okay, so now our sphere is falling down with the speed, and maybe let's increase the sphere size a bit more, and let's move him up and let's check. Okay, so here as you can see our sphere is squishing our soft body. Okay, and for creating these types of soft body we also have a constraint named vellum strut constraint. So if you add a vellum configure strut soft body, So let's add that. Okay, and let's move this whole setup up, and let's push this one down, and maybe push this one down a bit more, and let's select all of them and make them down. And now let's select this into the vellum constraint. So vellum strut has two constraints in it. So first we have the vellum cloth constraint. Okay, and after that it's generating these vellum strut constraints. So if I add a null in here, and let's view our constraint geometry, and here as you can see we have these strut constraint that is connecting opposite of these geometry. Okay, so these strut constraint will help preserve the volume of our geometry. Okay, and it is very fast to simulate compared to the our tetrahedral soft body. Okay, so in here let's connect this into our simulation, and let's remove this geometry into our merge node, and let's remove his constraint and also remove the collider pin. And here we have the geometry. Maybe let's put them in this side. So that's the geometry, and that's the geometry merge node, and that's we have these constraints. And let's set the display flag to vellum solver, and let's check. Okay, so here as you can see we have a soft body. So right now it's not preserving its shape as much. So let's go into the vellum cloth constraint. So in here we have the stretch stiffness, so it is already set to a higher value. So let's go into the vellum strut constraint, and into the vellum struts we have the stretch stiffness. So let's increase its stiffness to a higher value, and let's see the result. Okay, so here as you can see we have a soft body that is actually preserving its shape. Okay, and here as you can see, because we have all of these separate connected pieces, so now they are disconnecting from the geometry. So to fix that, let's go into the geometry, and let's first convert this into a VDB. So let's add a VDB from polygon node, and let's connect that. And here onto the VDB from polygon, let's lower the voxel size to 0.05 maybe, or maybe 0.02. Okay, and after that let's add a VDB convert node, VDB convert VDB. So let's connect this, and onto the convert VDB let's change the convert to polygons. So here we have the polygonal mesh. So now we have one single piece of connected geometry. Okay, and now let's connect this into the remesh node, and let's view the result. Okay, so now we have a triangulated mesh that is actually a one piece of connected mesh. Okay, and now let's set the display flag to the vellum solver, and let's view the result. Okay, so now we don't have all of these pieces exploding. Okay, and that's the basics way of creating the soft body simulation with the vellum. Okay, now let's take a look at the vellum pressure constraints. So let's create a geometry node and dive inside, and in here let's add a truss geometry rubber toy. Okay, and in here let's add a vellum configure balloon. Okay, so let's add that, and let's connect this into the vellum constraints. So here onto the vellum constraint, first we have the vellum constraint type is set to cloth to create a soft body behavior. And after that we have an vellum pressure constraint. Okay, so after that let's add an vellum solver for solving the soft body simulation. So let's add that, and here onto the vellum solver let's add a ground plane, and let's add the negative y offset into the ground plane, and let's hit play. Okay, so here as you can see we have a soft body that is actually looks like that it is filled with air or water. Okay, so here onto the vellum pressure constraint we can adjust the stretch stiffness, okay, to create a more stiff of the soft body. So let's change this to a higher value and let's see the result. Okay, and here as you can see we have this mesh, okay, distorted mesh. So to fix this let's add a remesh node. Okay, and let's uncheck the add shader option as well as disable the UV visualizer, and let's add a remesh node, and let's connect that. And onto the remesh let's change the target size to 0.07, and now let's see the result. Okay, so now we don't have all of these bending and the distortion of these points, but now all of these pieces are exploding. And to fix that let's convert this into VDB. Okay, so let's add a VDB from polygon node, and let's connect that. And onto the voxel size let's lower this down to 0.02, and after that let's add a convert VDB node, and let's connect this and convert it back to the polygons. Okay, and now let's connect this as a mesh into the remesh, and now let's view the result. Okay, so here we have a soft body. So let's go into the vellum pressure constraint and let's lower down the stretch stiffness to 100. Okay, and the power of the pressure constraint is actually come with when you actually animate its constraint values dynamically. Okay, so in here let's animate the rest length scale, and here as you can see our geometry is only initialized in the first frame. So if we animate this parameter, this animation won't be imported into the DOPS. Okay, to actually have any effect onto these parameter value, so we need to dive inside the vellum solver. Okay, and in here we have a node called vellum constraint properties node. So let's connect that, and let's connect this into the forces, and here onto the vellum constraint properties we can adjust the constraint properties, okay, by enabling that. So now here we can dynamically adjust the constraint properties. Okay, and to adjust the vellum pressure constraint rest length scale, so we need to activate this constraint group. Okay, so in here we have the option to output the group, so let's enable that. So here we have the group that is named stretch. So now let's dive inside, and in here to the vellum constraint property we have the option to enable the group, so let's enable that. And from here let's select the group, and here as you can see we have the bend and the stretch group. So these two groups are coming from the vellum cloth constraint. So let's go back, and in here we have the output group option turned on, so you can rename this group to know that which constraint you are working on. Okay, or let's disable the constraint, and also let's disable the bend constraint in here as well. Okay, and onto the vellum pressure constraint, let's maybe rename the output group and let's call this one pressure. Okay, and now let's dive inside, and in here let's select our pressure group. Okay, so in here now when we adjust these parameters, so now we know that we are adjusting the parameter for the pressure constraint. So in here we can adjust the stiffness. Okay, or in here let's set the rest length. Okay, so we are here setting the rest length to 1, and let's view the result. And here, as you can see, our geometry is expanding. Okay, so rather than setting the rest length scale manually, let's disable that and let's enable the rest length scale. So this is a rest length scale multiplier. Okay, so right now the scale multiplier is set to 1, which means we are using the currently rest length scale. Okay, so let's go into the frame 35 and let's add a key in here, and let's go into the frame 40 maybe after the 5 frame, and let's set the rest length scale to 2, and in here let's add a key, and let's go back and view the result. Okay, so here we are in the 35 frame, and here, as you can see, we have this balloon popping. Okay, so our geometry is expanding its volume, so we are filling the air. So maybe let's increase the rest length scale a bit more. So right onto the 40 we have the rest length of 2. Let's go into the 45 and let's change the rest length to 4, and let's add a key, and let's go back and let's see the result. Okay, so here we have a first scale, and now here we have this inflated geometry. Okay, so let's go back, and in here to actually use this simulation result onto our original high-res geometry. Okay, so up here we have this original geometry, so in here let's add a shader. Okay, and to transfer the animation of our this simulated geometry, let's add a node called point deform. So let's add a point deform node, and in here let's select our original mesh, this we want to deform, and the rest point lattice. So this is the rest point lattice and this is the animated geometry. Now let's see the result with the point deform and let's check. Okay, so now here, as you can see, we are transferring the result onto our original high-res geometry. Okay, and let's dive inside the vellum solver and onto the vellum constraint properties. So onto the 45 frame we have set the scale to 4. Now let's go into the frame 55 and let's change the scale to 0.3 maybe. Okay, and let's add a key in here, and now let's see the result. Let's hit play. So first we have this inflating of our geometry, and now we are reducing its volume. Okay, so that's the vellum pressure constraint. Okay, now let's take a look at the vellum shape match constraint. So let's create a geometry node and dive inside, and in here let's add a test geometry pig head. Okay, and in here let's change the option. In here uncheck the add shader, and let's disable the UV visualization, and after that let's add a remesh node to create a triangulator mesh. So let's connect that here onto the remesh. Let's lower down the size to 0.07. okay, and let's move the big head geometry up in the y-axis. So let's move him up, and after that let's add a vellum constraint node. So let's add a vellum constraint, and let's put this into the vellum constraint node, and onto the vellum constraint let's change the constraint type to shape match. Okay, and after that let's add a vellum solver, and let's connect that, and also onto the vellum solver enable the ground plane, and let's hit play. Okay, so here as you can see the vellum shape match constraint is trying to maintain the original shape. Okay, so it is used to create a rigid object. Okay, so here onto the vellum shape match constraint. So if we go into the help and into the contents, and let's go into the what's new Houdini section. Okay, and in here let's go into the vellum section, and onto the vellum we have the shape match constraint, and here we have a node. So it says that the older chipset architecture are not supported. Okay, so if we are using a graphics card with the older architecture, so this constraint might not work. So to fix that, let's go into the preferences and change your OpenCL device to CPU. Okay, so let's go into the edit preferences, and down here we have the miscellaneous, and from here we have the OpenCL device. Okay, so if your GPU is not supported, you can change this to CPU, and after that you have to restart the Houdini. Okay, so restart is required. Here as you can see the restart Houdini apply the changes. Okay, so that's the thing with the shape match that you need to know. Okay, and onto the vellum shape match we have the stiffness. So if we lower down the stiffness, and let's go back, and here as you can see by lowering down the stiffness we have a bending into our object. Okay, so to create a absolute rigid simulation, so we have a node called vellum transform pieces. Okay, so let's add a vellum transform pieces node. So it has 3 inputs. So here we have the constraint geometry and the vellum geometry, and this one requires the geometry to transform. So at this pin you can connect the original geometry. Okay, and let's set the display flag to the vellum transform pieces, and here as you can see now we don't have any deformation onto our original geometry. Okay, so that way you can get the absolute rigid simulation from vellum. Okay, so here onto the vellum shape match constraint we have the option to enable the plasticity. Okay, so if you enable the plasticity it will keep the deformation. Okay, so in here let's add a tube for a collider. So let's create the tube, and let's connect this into the collision geometry, and here onto the tube let's enable the end caps as well as adjust its radius. So let's lower down the radius and increase the height. Also let's change the center to move the geometry up, and let's change the center into the Z. Okay, let's add an offset in here, Okay, and now let's give an initial velocity to our pig head. So let's add a point velocity node. Here we have the point velocity. Let's connect that, and onto the point velocity let's change this to set to value, and let's give him in the z direction and a velocity. So let's change this to 13, and let's see the result. Okay, so here as you can see we have some deformation going on. So maybe let's rotate the pig. So let's add a transform node in here, and let's connect that, and here onto the transform let's add the rotation around the x-axis. Okay, so now we have the pig facing into the collider direction, and also maybe lift the geometry up, and also let's zero out the x but add a z offset. Okay, and now let's hit play. Okay, so here as you can see we have these bending. Okay, so now let's also maybe go into the collider and let's lower the radius down a bit more to create a thin tube. Okay, and let's check, and maybe let's also give him a higher velocity. So let's change this to 25, and let's check. Okay, so right now here as you can see we don't have any deformation. So no, we do have deformation but we don't have the plasticity. Okay, so it's retaining its original shape. So after the deformation it's coming back to its original shape. So let's go into the vellum shape match and let's enable the plasticity. Okay, and also let's increase the plasticity rate, and let's check. Okay, so now here as you can see we have the plasticity applied. So now the pig is keeping the deformation. Okay, so it's not returning to its original shape. So let's maybe increase the stretch stiffness. So let's change this to a higher value and let's check. Okay, and after that let's introduce another colliders in there. So maybe let's add these two boxes in here to squish the geometry in. So in here let's add a box and let's template the box. Okay, so here we have the box at the center. So let's adjust its size and make it thinner, and let's adjust the Y size and also increase the Z size, and let's also give him a offset into the X and into the Z as well. Okay, let's add a little bit more offset and to create a opposite side of our collider box. So let's add a mirror node in here. Let's add a mirror and let's connect this and template our mirror. Okay, so now here we have the second box. So now we can adjust this X. Okay, so let's animate this parameter. So about 55 frame, let's keep them here and let's add a key. And after that, and here if we scrub the timeline, here as you can see our simulation is cooking. So what we can do is click on this brain icon, so this will disable the dynamic simulation. Okay, so now here as you can see now we don't have this dynamic simulation, and it also says here into the viewport that the dynamic simulation is disabled. Okay, so let's add a key in here. Let's squish these down and let's add a key, and after that let's add another key, and after a few frames let's bring these boxes back and let's add a key, and let's view the animation. Okay, and now let's merge this with our collider. So let's add an merge node and let's merge this with this collider, and now let's enable the dynamic simulation by clicking on this brain icon. So now our simulation is enabled, and let's view the result. Okay, so first we have a first hit, and now these boxes came in here, and here as you can see we are squishing our pig head and it's retaining its shape. Okay, so if we disable the plasticity, so in here let's uncheck the enable plasticity. So now we have a normal soft body simulation. Okay, so here as you can see, after it's get hit and the colliders are gone, it will restore its original shape. Okay, so now we don't have the plasticity and it's returning to its original form. So let's enable the plasticity. Okay, so that's the vellum constraint node. Okay, now let's see how we can simulate the hairs, strings and wires with the vellum solver. So let's create a geometry node and dive inside, and in here let's add a sphere, and let's add a line for the simulation. So here we have the line. So now let's copy this line onto this sphere surface. So let's add a scatter sop, and let's connect the scatter onto the sphere, and onto the scatter let's lower down the number of particles, and let's add a copy to point sop to copy this line into the points. So let's connect the line and connect the points. Okay, so right now our line is not orientated, so for orientation let's use the point normal of the sphere. So let's add a normal to generate the normals. So let's connect that, and here onto the normal let's change the add normals to points. Okay, and now let's set the display flag to the copy to points. So the direction is not correct, so let's zero out the y, let's add the 1 into the z. Okay, so now we have the line in the correct orientation. So if I enable the points, here as you can see we have the line made of 2 points. So let's increase the number of points because we are going to simulate this line, so we need the geometry for bending. Okay, so now let's set the display flag to the copy to points. So now we have some points. So after that let's add a vellum constraint node, and let's connect that to generate the constraints. And here onto the vellum constraint we have the constraint type. So we have the option to set the hair constraint, and also we can set this to string constraint. Okay, so the hair and string constraint are the same, but the string constraint is a lighter variant of the hair constraint. Okay, so it's a bit faster. So let's connect that, and after that let's add a vellum solver, and let's connect the geometry and the constraints as well as the collision, and let's hit play. And here as you can see, our hairs are falling due to gravity. So in here let's add the collider. Okay, so let's use the original sphere as a collider. So let's connect this into the collision geometry as well, and let's hit play. Okay, so some of them are still falling, so let's pin these root points. Okay, so in here let's add a group node, and let's change the group to points. Let's call this group to pin, and in here let's use the point number 0, which means the very first point. Okay, so after that, when we copy the geometry, we will have the pin group. Okay, so let's go into the vellum string, and in here we have the option to specify pin points. So from here let's select the pin group, and now let's go into the vellum solver and hit play. And here as you can see, now we have all of these hairs pinned down. Okay, so right now we are using the group to pin these lines. Okay, so what if we were to simulate or animate the sphere? Okay, so if we animate this, we want this to follow the animation of the collider. Okay, so to fix that, let's go into the vellum constraint and let's not use the pin group. Okay, so in here let's add a vellum attached to geometry constraint. Okay, and let's connect that. And in vellum attached to geometry, we have the vellum constraint, and constraint type is set to attach to geometry. So from here we can enable the max distance option. Okay, so the points that are in this distance will be constrained together. So if we go into the vellum solver and into the visualize, and let's enable the attached to geometry constraint visualizer. Okay, so let's go into the vellum attached constraint and let's give him a little bit of distance value. And here as you can see, we have these constraints. So let's go into the visualizer and let's increase the radius. Okay, and here as you can see, all of these points that are in this distance are getting connected with the surface. Okay, so let's disable the attached to geometry constraint visualizer, and now let's hit play. Okay, so now here as you can see, we have these hairs sticking to the surface of the sphere. So now let's animate this sphere. So after that, let's add a transform node, and let's connect that. And onto the transform, let's give him the rotation around the y-axis. Okay, so in here let's add a sine function to add the sine wave. Okay, so let's type sine. So in the sine, let's use the $f, the current frame number. Okay, so now it will generate the sine wave. So if we hit play, and here as you can see, we have little bit of rotation. So let's increase the frequency of the sine. So here onto the $f, let's multiply by this by 20, and now let's check. And here as you can see, now we have increased the sine wave frequency, and now let's increase the amplitude of the wave. So to increase the amplitude, let's multiply this whole function. Okay, so maybe let's multiply this whole function by 70, and let's check. So now here as you can see we have the sphere rotating, but the frequencies may be too high. Let's lower down the frequency. Let's multiply by this by 10 and let's check. Okay, so this frequency looks good, and now let's view our result. Okay, so now here as you can see our hair are sticking to the animated geometry as well. So let's go into the transform node and let's copy this whole expression and let's paste this into the X rotation as well. And from this one let's increase the rotation, its amplitude. Let's change this to 90 and let's view the result. Okay, so some of the constraints are breaking, so we may need to adjust the max distance. Okay, because we have the initial rotation, so maybe let's increase this to 0.01. Okay, and let's check. Okay, so now we have all of these hairs pinned together. Okay, and let's also copy this whole expression and maybe let's add this into the translate X, and in here let's remove the amplitude value which is too high and let's check. And let's go into the vellum attached to geometry constraint and let's increase the distance value. Okay, so let's change this to 0.1 maybe and let's check. So these hairs are too far away. Okay, so we maybe need to go into the transform and let's remove this expression. So let's delete this channel and let's zero out the X rotation. Okay, and also let's remove the frequency multiplier. Okay, and now let's check. Okay, so here as you can see now we have the movement in the X. Okay, and after that let's give these hairs a thickness. So let's add a polyvar in here and let's connect the geometry output into the polyvar, and onto the polyvar let's the wire radius. Okay, and let's merge our original geometry. So let's add a merge and let's merge these hairs with the sphere and let's check. Okay, so here we have the hair simulation. Okay, with the vellum. Now let's see how we can tear a cloth with the vellum. So let's create a geometry node and dive inside, and in here let's add a planar patch to create a planar patch, and let's go into the planar patch and let's lower down the Y size of the patch, and also let's increase the resolution of the geometry. So let's go into the edge length and let's lower this down to 0.05 maybe. Okay, so after that we need to fracture the piece of cloth. Okay, so for that let's add an edge fracture node. So not the edge flip but the edge fracture node. Okay, so let's select that. Let's connect this into the edge fracture and here onto the edge fracture. So here we have some initial pieces. So right now it is set to 10. So if I enable the primitive piece attribute and click on this visualizer, so here we have these different pieces. So let's add an exploded view for visualization. So let's add that and connect this into the exploded view. So here we have these cloth fractured pieces. Okay, so into the edge fracture we can set the number of pieces. Okay, so let's lower this down and let's delete the exploded view and let's uncheck the primitive piece attribute. Okay, so after that let's add an vellum cloth constraint to convert this into a cloth simulation. So let's add an vellum configure cloth node and let's connect that, and here onto the vellum cloth let's pin this side group. So first let's go into the planar patch and let's enable our left seam group. Okay, and let's go into the vellum cloth constraint and into the pin to animation let's select our planar patch left seam group. Okay, so now here we have this pin visualized. So after that let's add a vellum solver. So let's connect this into the cloth constraint and let's view the result. And here as you can see our geometry is right away falling apart. So to stitch these unconnected pieces we have a constraint called vellum weld. So let's add a vellum weld points and let's connect that, and here as you can see the vellum, we have the vellum constraint and the constraint type is set to weld points, and here as you can see it's looking for the unconnected points and stitching them together. Okay, so let's go into the vellum solver and now let's hit play. Okay, so now here as you can see our geometry is stitched together. So let's dive inside, and in here let's add a pop force to create the wind. So let's add a pop force and let's connect that. Now to the pop force let's give force in the x direction. So let's change this to 13. Let's increase the amplitude to 7 and let's hit play. Okay, so here as you can see let's go back and let's enable the real-time toggle for the real-time playback. Okay, so to fracture these pieces, okay, so right now here as you can see our constraints are not breaking. So let's go into the vellum weld constraint, and in here we have the option to break the constraints. So let's enable the breaking. Okay, and let's hit play, and now here as you can see when we have the enough stretch stress it will break. Okay, so right now it's not breaking and we need to set the wind into the x direction. We are setting in the z. So let's dive inside, let's zero out the z value but add the wind into the x direction. Okay, and let's hit play. Okay, so let's maybe increase the wind speed. So let's increase this to 26 and check. Okay, so the wind speed is still not enough, so maybe let's go back onto the vellum weld constraint and let's lower down the threshold value. So let's change this to 0.05 and let's check. Okay, so now here as you can see our cloth is tearing apart. Okay, so let's go into the edge fracture and maybe let's increase the number of fracture pieces. And now let's check the result. Okay, and let's increase the threshold. Let's change this to 0.1 again. Okay, so 0.1 threshold is maybe too high, so let's lower this again to 0.07 and let's check. Okay, so now we do have the cloth tearing, and here as you can see, because we have some unconnected points, so we have this faceted geometry look. So let's add a vellum post process node. So post process, and let's connect that. And here onto the vellum post process, we have the apply welds option turned on. And let's also add the subdivision. Let's change this to loop and check. And now here as you can see, now we don't have these unconnected seams. So if I uncheck the apply welds, and now here as you can see, we have these seams. So let's check this on to create a single cloth. Okay, and now it's tearing. And here onto the edge fracture, we have the option to specify the fracture curves. Okay, so in here let's disable the initial pieces, and if I enable the primitive piece attribute, so now here as you can see, now we don't have these fracture pieces. So in here let's add a draw curve node. So let's add that and connect it into the curve. And here onto the draw curve, let's uncheck the width attribute, the color and the stroke attribute. And onto the draw curve, press enter. Okay, and let's draw a curve. And let's go into the edge fracture, and let's uncheck this again to visualize. Okay, maybe we need to enable the initial pieces. And now here as you can see, Houdini viewport is refreshes, and we have the fracture line where we have draw the curve. So let's draw another curve. Let's add curve in here. Let's add in here as well, and let's draw the curve in this direction as well. Okay, so here as you can see, we are really directing the fracture lines with the curves. Okay, and now let's set the display flag to the vellum post process, and let's go into the edge fracture and disable the piece attribute. Okay, and let's view the result. Okay, so that's how you can fracture cloth with vellum. Okay, now let's take a look at the vellum brush node. So let's create a geometry node, and let's dive inside, and in here let's add a truss geometry rubber toy, and let's convert this one to a vellum strut soft body. So let's add a vellum configure strut soft body constraint, and let's connect that. And after the constraints, let's add a vellum brush node. Okay, so here we have the vellum brush. So vellum brush is an interactive solver. So let's connect this, and let's set the display flag to vellum brush. Okay, and select the vellum brush node and hover over to the viewport and press enter on your keyboard to have access to its manipulators. Okay, so now we are in the vellum brush tool, and now if I draw here, as you can see, I am simulating the soft body. Okay, so here we have some shortcuts for adjusting the radius. Okay, so if you scroll your mouse wheel, you can adjust the brush radius. Okay, so if you right click here we have the option to change the shape of the brush. So right now it is in the screen space. You can change this to surface, okay, or you can change this to volume, okay. And let's grab our geometry, and in here we have the mode. So right now it is set to brush mode. Let's change this to drag mode. So now I can drag the geometry, and here as you can see we have this mesh breaking, and that is because we didn't converted our mesh into triangles, okay. So let's add a test geometry pig head instead, okay. And let's remove the rubber toy, and into the pig head let's uncheck the add shader option, and also let's hide the UV visualization, and let's add a remesh to create a good triangulated mesh. So let's connect that, and onto the target size let's change this to 0.05, and let's connect this into the cloth constraint, and let's go into the vellum brush, and to update the newly changes let's click on this reset all changes option, okay. So now we have our new geometry loaded. So now let's select the vellum brush and press enter, okay. So now here as you can see we have a much better geometry, okay. So right now our geometry is not holding that much of volume. So let's click on reset all changes, and let's go into the vellum strut constraint, and onto the stretch stiffness let's increase the stretch stiffness, okay. And let's go into the vellum brush, and let's click reset all changes one more to update the newly changes setting. And now let's draw, okay. And now here as you can see we have a very stiff soft body, okay. So right now I am in the drag, so let's change the shape to surface or maybe screen space, and let's increase the brush size, okay. So you can really interactively place your soft body, okay, or you can set dress the cloth, okay. So that's a very interactive solver. So now in here let's create a planar patch. Let's add a planar patch in here. So the planar patch is already in triangulated. So let's go into the planar patch and change the orientation to ZX and move the patch up, okay. And also let's increase the patch size, okay. And after that let's connect this into a cloth constraint, and let's use our pig as a collider geometry. So let's connect this into the collision geometry, okay. And here as you can see we have a pig down here. So let's go into the vellum brush and click on reset all changes, okay. So let's increase the patch size a bit more. So let's go into the planar patch, set the display flag to the planar patch, and let's template our pig, and let's scale the patch size up and also move the patch up, okay. And let's not use the remesh, let's use the original geometry, okay. Now let's go into the vellum brush, click reset all changes and press enter, okay. And now let's drag the cloth down, okay. So here as you can see our collider is working, okay. So let's drag the cloth up maybe and move this piece up. And if you right click, we have the option for brushing. Okay, and also we have the option to contract or expand. Okay, so if you press and hold, now our cloth geometry is contracting. Okay, and if you right click, now we have the option to rotate, so let's click that. Okay, and if you press and hold, and here as you can see, we are applying the rotation into the simulation. Okay, and let's also change this to drag, and to drag our cloth up. And also we have the option to generate the pins. So the key is that shift plus middle mouse button. So hold down the shift and middle mouse button, and here as you can see, we have generated these pins. So now if I move my cloth, so this will be straight pin into the state. Okay, so if you want to drag these pins, press and hold the middle mouse button and drag. Okay, so now we are dragging the pins. So in here, let's add another pins and middle mouse button and drag. Okay, and to remove the pin, we have the control plus middle mouse button. So hold down the control and middle mouse button to remove the pins. And now let's use these pins to move the cloth. Okay, and you can also come to the vellum brush and click reset all changes to reset the simulation to the initial state. Okay, so that's the vellum brush node. Okay, now let's talk about vellum grains to create the granular simulation like sand and snow. Okay, so let's create a geometry node and dive inside, and in here let's add a test geometry pig head. Okay, and let's move the pig head geometry up. Okay, and to fill this geometry with grain particle, we have a node called vellum configure grain. Okay, so here we have the vellum configure grain. So let's add that, and let's connect this into the vellum configure grain. And onto the vellum configure grain, let's check the create points from volume option to generate the particles. Okay, so here we have these grains particles. So here we can adjust the number of particles. Okay, so let's lower this down to 0.05 and let's check. Okay, and here as you can see, we have these grains particles in regular grid arrangement. Okay, so here we have the method. We can change this to sphere packing. Okay, so now it is packing these particles with this minimum sphere radius. Okay, so let's change this to regular grid and let's enable the jitter scale. Okay, to randomize the distribution of the grains particles. Okay, so now we don't have these regular grids. So now let's add a vellum solver. So let's add a vellum solver and connect this, and onto the vellum solver let's enable the ground plane and let's hit play. Okay, so here we have the very basic grain simulation with vellum. Okay, and to add the attraction weight to create a wet sand effect, so let's go into the vellum constraint and onto the physical properties. So here we can adjust the mass and the friction. So let's add an attraction weight. Okay, so attraction weight is set to 1, and now let's check. And here, as you can see, our simulation looks exactly the same, and that is because here onto the vellum solver, let's go into the advanced and onto the grain collisions, and here we have the attraction weight. So this value will be multiplied with the source attraction weight. So let's change this to 1 to have a wet sand effect. And now let's check. Okay, so here, as you can see, we have a very jittery simulation. So let's increase the sub-steps. So let's go into the solver and let's increase the number of sub-steps. Let's change this to 5, and let's lower the constraint iteration, okay, to have a faster simulation. And let's hit play. Okay, so here, as you can see, now we have an attraction weight, but some of our particles are exploding. So let's go into the vellum constraint and let's lower down the attraction weight. So let's lower this down to 0.1 maybe, and let's check. Okay, so let's increase the attraction weight a bit more. Let's change this to 0.5 maybe, and let's check again. Okay, so here you can see we have the wet sand. Okay, and onto this vellum solver that is available on the SOP level, we don't have the enough options for the grains. Okay, so whenever you are working with grains, so you have a very basic control with this vellum solver. So let's create a vellum solver in our own. So let's add a .NET, .network, and let's dive inside. And in here, let's add a vellum solver, and let's connect this. And in here, let's connect the vellum object node, and connect this. And here onto the vellum object, let's select the initial geometry and the constraints. So let's go back, and in here let's add an null for the constraint and the grains. So let's call this one constraints. Okay, and let's duplicate this null and connect this here, and let's call this one grains. Okay, and now let's dive inside the .NET onto the vellum object. Let's select the initial geometry and select our grains, and also let's select our constraint geometry. And in here, let's add a ground plane for the collision. Let's add a merge, and let's merge the ground plane with the vellum solver. And onto the effector relationship, let's change this to mutual, and also add a gravity force, and let's connect that. And now let's hit play. Okay, so here we have a grain simulation. So let's go into the ground plane and let's uncheck the display proxy geometry to hide the ground plane. So we still have the ground plane, but we are not visualizing it. Okay, so let's go into the vellum solver and onto the advanced and the grain collisions. So here, as you can see, we have all of the options for the grains. Okay, so here we have the attraction weight and the attraction. So let's add an attraction weight of 0.1, and let's check. And let's also go into the common and increase the number of sub-steps. So let's change the sub-steps, and let's lower down the constraint iterations. And now let's check. Okay, so here, as you can see, we have the wet sand. Okay, and onto using this solver, we have all of the settings available for the grains. Okay, So let's go back and here onto this vellum solver. So here we are creating the attraction weight attribute. So you can use the attribute noise and the attribute warp to randomly create the attribute weight. Okay, and it will work. So let's go into the vellum solver and let's zero out the attraction weight to create a dry sand. Okay, so here as you can see, now all particles are sliding too much onto the floor. So let's go into the forces tab, and in here we have the friction. So this is the friction for the tangential velocity, which means the sliding. So let's increase this to 0.5 and let's check. Okay, so now here as you can see, now we don't have as much sliding. Okay, and let's go into the solver tab, and for the accurate result you need to increase the substeps as well as the constraint iteration. Okay, so here if I change the constraint iteration to 1 and let's check, and here as you can see we are losing the volume. Okay, so maybe if I change this to 0 and here it will be clearly visible. Okay, so here as you can see now we don't have the collisions between the grain particles. Okay, and if I change this to 1, so here we have the collisions, but now we are losing a lot of our volume. So if I increase this to 100 and let's check, so now the simulation is slow but it will be accurate. And now here as you can see we have the lot more volume into our particles. Okay, so you need to increase the constraint iteration as well as the substeps for more accurate results. Okay, and you can also use the mass attribute to activate these grains particles as well. So after, let's remove this constraint and also remove the top net. Okay, and in here you can create the growing attribute. Okay, so for this example let's create a box. Okay, and let's template the box, and onto the box let's increase the box uniform scale. Okay, let's increase it even more, and let's change the center. Okay, and after that let's add a transform node, and let's connect this, and here onto this transform node let's move the box up. Okay, so outside of our big head region. Okay, so in here let's add a keyframe, and let's go into the frame 73 maybe, and let's bring this all the way down, and let's add a key. Okay, so in here let's create an attribute by adding an attribute triangle, and let's connect that, and in here let's create a float named mass. Okay, so let's set its mass to 1, and now let's transfer this attribute. So let's add an attribute transfer node, and let's transfer this into our grains particles. So here we have the attribute, and onto the attribute transfer let's uncheck the primitive attributes and only select the mass. Okay, and now let's connect this, and let's set the display flag. Okay, and let's untemplate the big head geometry, and onto the vellum constraint. So we are setting the mass to 0.1. So let's set the mass to 0. Okay, and let's hit play. So we still have animation. So if we go into the geometry spreadsheet and look at the mass, and after the attribute transfer, here as you can see we are setting the mass to 1, and that is because onto the condition we have a very large distance threshold. So let's lower this down to 0.1 maybe, and now we don't have the mass. Okay, so now let's hit play. Okay, so our particles are not moving. So to dynamically import this attribute, we need to dive inside the vellum solver, and in here let's add a pop wrangle node, and let's connect this into the forces, and onto the input let's use the SOP, and from here let's select the attribute transfer node, and from here let's set the mass, so float at mass, and let's use the point function to import the point attribute. So geometry stream is 0, which means it's self, and the name of the attribute, so the name is mass, and for the point number let's use the @btnum for the current point number. Okay, and now let's go back and view the result. Okay, so distance threshold of 0.1 may be too low, so let's lower this down to 0.5 and let's check. Okay, so we are still not importing, so let's go into the attribute transfer and let's visualize our mass attribute, and let's hit play. Okay, so we are still not transferring the mass attribute, so let's increase the distance threshold and let's check. And here as you can see we are skipping some of these areas, and that is because our box is hollow. So let's add points inside of this box, okay, for better contact area with our particles. So after the box let's add a points from volume node. Let's connect this, and here we have the points, and now let's visualize the mass attribute. Okay, so now we are setting correctly, so let's go back, let's lower down the distance threshold and let's check. Okay, so now we are transferring the attribute correctly, so let's click on this eye icon and click on the mass to hide the visualizer, and let's set the display flag to vellum solver and let's hit play. And here as you can see we are dynamically importing the mass attribute to activate the grains. Okay, so that's how you can work with the vellum grains. Okay, now let's talk about flip fluids. So let's create a geometry node and dive inside, and in here let's add a truss geometry big head, and let's create a dop network, and let's set the display flag to the dop net and let's dive inside, and in here let's add a flip solver. Okay, so here we have the flip solver, so let's connect this into the out, and here we need to connect the flip object. So let's add a flip object and let's connect this into the first input, and here as you can see we have the default cube geometry. So if we go into the flip object and onto the initial data, here as you can see we have the saw path filled with the default box. Okay, so to import our pig head into the simulation, so let's go into the flip object and onto the initial data, and let's select our pig head geometry. Okay, so let's select that and hit accept. Okay, so here we have the pig head, and right now it is visualized in the sprites. So let's go into the guides of the flip object. Okay, so here we have the guides. So that's the particles and that's the surface. So right now the particles guide is enabled. So here we have the corresponding tabs to adjust the visualization. Okay, so let's go into the particles tab, and here the visualization is set to sprites. So let's change the visualization to particles. Okay, so here we have the flip particles. Okay, and onto the top we have the particle separation. So this will control the number of particles. So let's lower this down to 0.05. Okay, so now here as you can see we are generating more particles. Okay, and maybe let's change this to 0.1. Okay, and if we zoom out, here as you can see we have this box. So that's the flip domain. So our flip simulation will live inside of this domain. So we can adjust the domain size onto the flip solver node. So if you go onto the flip solver and onto the volume motion, so here we have the volume limits. Okay, and here we have the visualization color. So let's change this to an blue, dark blue color to have better visualization. Okay, and here we can adjust the limits size. Okay, so now we are reducing the domain size, and let's go back into our pig head geometry, and let's scale up our pig head geometry. So let's set its scale to 5. Okay, and let's dive inside. So now we are generating a lot more particles. Okay, and now let's hit play, and here as you can see nothing is happening because we don't have any forces. So let's add a gravity force in here by creating a gravity force and connect that, and now let's hit play. Okay, so here we have the particles moving down due to the gravity. Okay, and here you will see that after reaching the limits our particles are deleting. So let's go into the flip object and let's check the closed boundaries. Okay, so now our domain boundaries will act as a collider. Okay, so now let's hit play and check. Okay, and here onto the particle visualization, if we go into the visualizer, here as you can see we are using the speed ramp. Okay, and here as you can see now our simulation is colliding with this domain range. Okay, and here we have the speed visualizer. So here we have the ramp, and we are calculating the speed from the particles velocity, and here we have the velocity range. So let's increase the velocity range. Okay, to adjust our gradient color. So now let's go back onto the first frame and let's enable the real-time playback and let's check. Okay, so here we have a very basic flip simulation. Okay, so if you want the continuous emission of the flip particles, okay, right now we are initializing the particles here onto the initial data. Okay, so we are initializing this on the first frame, and then the simulation will solve these particles. Okay, so for the continuous emission, so here we have the sourcing, so we need to import the source in here every frame. So for that, let's add a volume source node. Okay, so you can import the flip with the volume source node. Okay, so let's connect this here onto the volume source. We have the input, it is set to SOP. Let's use the first context geometry, and let's go back and connect this into the first context, and let's dive inside. And in here we have the initialization, it is set to source smoke. So let's change this to source flip. Okay, so now let's go into the flip object and let's remove the initial SOP path. Okay, so because now we are importing the source with the volume source node, so we don't need to initialize it here. So let's remove the SOP path expression. Okay, and here as you can see, our source has not been imported, and that is because we need to convert this into these particles. Okay, so in here let's add a flip source node, so flip top source. Okay, and let's connect that. So the flip top source node will convert our geometry into particles and create a surface VDB. Okay, so we have the particles as well as the surface VDB. So flip use these two, surface VDB and as well as particles, to create the fluid simulation. Okay, so now let's go into the topnet and dive inside, and here as you can see, now we are importing our pig head geometry as a source. And now let's hit play. Okay, so here as you can see, now our pig is emitting the fluid inside of our simulation. Okay, so now let's go back and reduce the number of particles. So right now our simulation is working slow, so let's go back onto the flip source, and in here let's increase the particle separation. Let's change this to 0.2 maybe, and let's dive inside and check. Okay, so here onto the flip object, we need to link this parameter with this particle separation. Okay, so let's change this to 0.2 and let's check. And now here as you can see, we have a very fast simulation. Okay, so now let's give him an initial velocity to these particles. Okay, so let's go back, and after the flip source, let's add a point velocity node. Let's connect the point velocity, and onto the initialization, let's set this to value, and let's give him in the negative y-axis velocity. So let's change this to -1, and also let's add a curl noise into the velocity, and let's check with the results. Okay, so here our velocity result is not very visible, so maybe let's go back, and here onto the point velocity, let's give him velocity into the x direction. So let's zero out the y, and onto the x, let's change this to 15, and let's dive inside and check. Okay, so here as you can see, our particle velocity is working. So 15 is maybe too high, so let's change this to 5, and now let's check. Okay, so here we have the velocity onto the side. Okay, and now let's go back, and onto the point velocity, let's adjust the curve noise scale. So let's set this to 5 and let's check. Okay, so here as you can see, now we have this noised up velocity. Okay, and we are continuously emitting the flip simulation. Okay, and filling our entire domain with the water. Okay, so let's rewind and check the results. Okay, and let's go back, and here onto the SOP level we do have a flip solver like the other solvers. So in here let's add a flip solver. Okay, so here we have the flip solver, and it has these 3 inputs that are necessary for it to work. So first let's add a flip boundary node, and let's connect that. Okay, so here onto the flip boundary, let's connect this into the source, and this is the container and this is the collision. Okay, and in here, and for flip boundary we need another node, and that is called the flip container. So let's add that. So let's connect this into the source, and this to container, and this to the collision. Okay, so if we set the display flag to the flip solver, so nothing happened. So let's connect our big head geometry into the source. Okay, so here onto the flip boundary, the last input is for the sourcing, so let's connect that, and here we have the big. Okay, and let's hit play, and here as you can see we are continuously emitting the flip. Okay, so let's go into the flip solver and onto the visualization. So here we are visualizing the particle as sphere, so let's uncheck that. So now we have these particles. Okay, so here onto the flip container, so we have the option to set the bounds. So let's increase the bounds. Okay, so now let's hit play. Okay, so after reaching the bounds, our particles are cutting off. So let's go into the flip solver, let's go into the collision tab, and in here we have the option to enable the ground plane. So let's add a ground plane. Okay, and let's move the ground plane position down. Okay, and now let's hit play, and here as you can see the particles are colliding with the ground. Okay, so if you want the particles to only initialize and emit for first frame, so we need to go into the flip boundaries, and here we have the option to activate our source. So here onto the activation, let's add an expression $FF if our current frame is equal to 1. Okay, so now we are only activating this onto the first frame, and now let's hit play, and here as you can see now we don't continuously emitting the fluid from the source. Okay, so that's the basic of the flip simulation. Okay, now let's talk about flip tank to create a filled water tank. So let's create a geometry node and dive inside, and in here let's add a particle fluid tank. Okay, so let's add that. So the particle fluid tank will add the particles in a box. Okay, so here onto the particle fluid tank we can specify the water level. and we can specify the particle separation to generate more or less particles. And in here we can set the tank size. Okay, and let's increase the flip tank size. Okay, and also let's increase the Z size as well, and let's make this flip tank sit onto the floor. So let's copy this Y size. Okay, copy parameter and onto the center Y. Let's in here say paste relative reference. Okay, so now we are using the same size as the Y size. So after that, let's multiply by this 0.5 to get the half value of the Y. Okay, so now if we change the Y size, our flip tank will sit onto the floor. Okay, so let's increase the Y size and also let's increase the water level. Okay, so let's adjust the water level to have more particles, and let's also adjust its X size. Okay, and after that let's create a DOP network. So in here let's add a DOP network, and let's connect this into the first input and dive inside the DOP net. And in here let's add a flip solver, and let's connect this into the output. And in here let's add a flip object, and let's connect this here onto the flip object. Let's initialize this with our particle fluid tank. Okay, so here onto the initial data, let's go into the SOP path and let's select our particle fluid tank, hit accept, and here as you can see our tank has not been imported, and that is because the input type is set to surface SOP. So here the flip object is expecting a surface geometry. Okay, so let's change this to particle field. Okay, so now here as you can see we have our particles imported. So let's go into the guides and onto the particles tab of the guide and change the visualization to particles. Okay, and now let's hit play and let's add a gravity force. Okay, in here let's create a gravity force and let's connect this, and now hit play, and here as you can see our flip tank particles are falling due to the gravity. Okay, and here we have the domain. So let's go into the flip solver and onto the volume motion. So let's link this domain size with our flip tank. Okay, so here onto the particle fluid tank, let's copy this parameter, and let's dive inside, and in here let's add a paste relative reference. Okay, so now we have the exact same size domain. So here onto the Y size, let's delete this channel. Okay, so we will set the Y size on our own inside of the flip solver. So let's increase the Y size, and let's also copy this parameter and onto the center, paste relative reference, and for this reference let's multiply by this 0.5. Okay, so now it will sit perfectly onto the floor. Let's change the visualizer guide. Okay, so now let's hit play. So our particles are getting deleted. So let's go into the flip object and check the closed boundaries and hit play. And now here as you can see our particles are colliding with the boundaries. So we need to also link the particle separation. So let's copy this parameter And let's go into the particle fluid tank, and in here let's paste this into this particle separation. So let's in here set paste relative reference. Okay, so now we are generating more particles. So maybe let's lower this down to 0.15 maybe, and let's check. Okay, so now our flip tank is working fine. So in here let's add some collision geometry. Okay, so for that let's create a rock geometry in here. So let's add a sphere and set the display flag to sphere, and let's change this to polygons, increase the frequency. Okay, and let's also increase the size of our sphere, and let's add a mountain node, and let's connect that into the mountain node. So let's go into the mountain node parameters, and let's adjust the amplitude, and also let's adjust the element size, and also let's go into the sphere and let's increase its X size. Okay, and here onto the mountain node let's change the noise type to Worley cellular. Okay, so this will create a rock like noise, and here as you can see. So let's go back and let's increase the frequency to add more divisions. Okay, so let's in here let's reduce the size. Okay, so that is looking more like a rock. So now let's transform this rock up. So let's add a transform node, or maybe let's add a copy transform node. So in here let's add a copy and transform, and let's connect this, and in here we are generating 2 copies. In here let's add the translation in the Y as well as add the translation in the X. Okay, and maybe let's generate these 3 copies, and let's add a transform node at the end, and let's connect that, and here onto this transform node let's push this rock geometry up. Okay, and let's template our particle fluid tank, and here as you can see we have very big rock sizes. So let's go into the sphere and let's adjust the uniform scale. Okay, so the size of 3 may be fine. So now let's go into the copy and transform node, and in here let's adjust the translation in the X translation as well. Adjust it more to bring all of these rocks a bit closer. Okay, and after that onto this transform node let's make this one into the sides, make this side even further. Okay, and now let's add an assemble node to create an packed geometry. So let's connect that, and here onto the assemble let's check the create packed primitive. Okay, so now we have 3 packed primitives. So now let's connect this into the second input of our .NET, and let's dive inside, and in here let's create an RBD packed object and a rigid body solver. So let's connect this into the packed object, and onto the RBD packed object let's select the geometry source. So it's set to SOP. Let's use the second context geometry. Okay, and let's add a merge in here, and let's merge this with our flip solver, and onto the merge let's change the effector relationship to mutual, and let's connect the gravity at the last. Okay, and now let's hit play, and here as you can see we have these rocks falling, and these rocks are falling very slow, so we may need to adjust the position of these rocks. And here they are touching the particles fluid. Okay, and here as you can see the particles fluid velocity is also affecting the rocks. So let's go into the RBD packed object, and in here we can set this activation attribute. Okay, so let's go back, and in here let's add an attribute wrangle. Okay, and let's connect this, and onto this wrangle let's create an attribute. So let's create the attribute active. So in here the active is an integer attribute, so I, and the attribute name which is the active, so let's set this to 0. Okay, so now it means that our geometry is not an active object. So if I hit play, here as you can see the forces are not affecting the rocks. Okay, so what we can do, we can dive inside the .NET, and here onto the RBD object let's give him an initial velocity. So let's add a downward velocity of -10 maybe, and let's check. We need to go back onto the first frame and let's check. Okay, so because they are not active, so these initial velocities are not working. Okay, so let's zero this out. So what we can do, we can go into the merge, and let's select this one onto the up. Okay, so we are reorganizing the node graph into the merge. So here onto the merge, the effector relationship is set to mutual, so let's change this to left input affects the right input. Okay, and let's go back, and in here let's disable the attribute wrangle. So now we have these active rigid bodies, and let's check. Okay, so now here as you can see these rocks are now affecting the particles, but the particles are not affecting these rocks. So in here let's add a ground plane for the collision. So let's add a ground plane in here, and let's add a merge, and let's merge the ground plane down here, and onto this one let's change the effector relationship to mutual. Okay, and now let's check. So the rocks won't go into infinity, so now they will collide with the ground plane. Okay, so maybe let's go back and let's increase the water level. So let's go into the geometry level, and in here we have the particle fluid tank. So let's increase the water level as well as Y size. Let's increase the water level even more, and now let's set the display flag to .NET, and let's see the result. So here we have these rocks falling down. Okay, and they are affecting the particles. So let's go into the rigid body solver, onto the RBD object. Let's give him initial velocity. Okay, so now they are an active RBD objects, so now this initial velocity will work. So let's give him an initial velocity of -10 maybe, and let's check. Okay, so now here as you can see these are falling down fast, and we have a splash in the particles. So maybe let's increase this velocity even more. So let's change this to -25 maybe, to create a much higher impact onto our particles. Okay, and now here, as you can see, we have a huge collision, and they are escaping these boundaries. Okay, because we have the higher velocity, so they are sliding all over onto the floor, these rock geometry. Okay, and let's simulate this few frame, and now let's go back onto the first frame and let's view the result. Okay, so here we have the big splash. So here onto the flip solver, you can also use the particles pop forces to drive the flip particle simulation. So in here, let's remove this merge, okay, for now, and let's remove this from here as well, and let's connect this into the gravity, and let's connect this into the out. Okay, so let's go back and maybe let's adjust the water level. So here onto the particle fluid tank, let's lower down the water level to 3 units. Okay, and now let's dive inside the top net, and in here let's add a pop access force. Okay, and let's connect this into the particle velocity, and here onto the pop access force, let's increase the radius as well as the height. Okay, so let's hit play. So here we have the guide, so let's go into the pop axis and let's move the access force radius, this fall of up sphere. Okay, and maybe let's place this around here, and let's increase the radius as well as the height. Okay, and let's also change the center to move him up. Okay, and let's hit play. Okay, so here, as you can see, the particles are rotating around the axis. So here onto the pop access force, let's go into the speed. So here we have the orbit speed. Let's change the orbit speed to 5 to create a more dramatic force. Okay, so here, as you can see, the pop access force is affecting the flip particle simulation. So in here, let's increase the lift speed. So let's change this one to 5, as well as the suction speed. Let's change this to 5, and let's see the result. Okay, so the particles are now lifting up and they are rotating around the axis. And here, as you can see, we have a very cool water simulation. Okay, so let's check, and maybe let's go into the shape tab and let's change the center to bring the center down, and let's check again. Okay, so that's, we have the water fountain. Okay, so maybe let's lower down the lift speed. Let's change this to 2, orbit speed to 2, as well as the suction speed to 2, and let's check again. Okay, so particles are now lifting up and they are rotating around the axis, and maybe let's increase the lift speed. Let's change this to 4 and check again. Okay, so now they are lifting upward, our particles, and now they are, after they reaching the limit of the shape, now they are coming down due to the gravity. Okay, So in here let's add a pop force node to add a wind. So here we have the pop force node, and let's merge this with the axis force to use both of these forces. So let's connect this and connect this, and here onto the pop force let's increase the noise amplitude. Okay, let's change this to 5 and hit play. So here as you can see we have the disturbance in the particles. So maybe let's adjust the swirl size. Let's change this to 3 and let's check. So now we have these bigger swirls. Okay, and here we have the noise into the fountain. Okay, so now it is not as smooth as it was before. So maybe let's adjust the visualization. So let's go into the flip object and onto the particle visualization. Let's increase the velocity range. So let's increase the range. Okay, and now let's view the result. Okay, so that's the particle flip tank. Okay, so you can create this filled fluid tank effect with the particle flip tank. Okay, so maybe let's enable the collider in here as well. So let's connect this into there. Let's merge this, and in here let's organize the ports because we have the left input affect the right inputs. Okay, so it must be in the correct order. And let's also add the ground plane in here as well. Let's add this, and this one is set to mutual, so this doesn't matter. Okay, so now let's check. Okay, so now we have these stones and we have the wind velocity as well as we have the particle forces, particle axis forces. Okay, so that's how you can set up the particle flip tank. Okay, so let's stop this here and let's rewind and let's play it again and see the result. Okay, now let's talk about the flip fluid's viscosity to create the viscous fluids. So let's create a geometry node and dive inside, and in here let's add a sphere. Okay, so this is the sphere that we are going to use for the emission. So let's move the sphere up. Let's change the center. Okay, and in here let's add a trace geometry shader ball. Okay, so let's use this geometry as a collider. So here onto the uniform scale, let's set the scaling of the shader ball to 3, and let's set the display flag to the sphere node, and let's template the shader ball. Okay, and we need to change the center of our emitter, and let's move the sphere up. Okay, and after that, here onto the sphere, let's add a flip dop source node, and let's connect this. And here onto the flip top source we have the particle separation, so we will link this with the flip object particle separation. Okay, so in here let's add a dop network. Let's connect the dop network, and let's connect this one to the first input, collider to the second input, and let's dive inside, and in here let's add a flip object and a flip solver, and let's connect the flip object to the flip solver, and let's add a gravity force in here. Let's connect this, and let's import our shader ball sphere for static object. So let's create a static object in here, and onto the static object let's select the saw path. So from here select the shader ball, okay, and now let's add a merge node, and let's connect this and the static object, and into let's organize the static object, okay, and here we have the effect relationship, left affect the rights, okay. So here onto the flip object let's remove this initial default fluid. So let's remove this saw path, and let's import our source with the volume source node. So let's add a volume source node, and let's connect this into the sourcing, and onto the volume source let's choose the input to the first context geometry, and onto the initialization let's initialize this to source flip, okay. So now it will import the particles as well as the surface field, okay, from the SOP level. So let's go into the flip object, and onto the guides let's go into the particles guide and change the visualization to particles, okay. And now let's link this particle separation. So let's copy this parameter, and onto the flip source node let's paste this into the particle separation. So paste relative reference, okay, and now let's dive inside and hit play, okay. So we have a very big domain. So let's go into the flip solver and onto the volume motion. So here we have the flip domain. So first let's change the color of the guide, and let's change the box size. Let's change the size to 10 by 10 by 10, okay, and let's see, and let's move the box center up, okay. So maybe let's change this to 6, and let's add this 3, okay. So now it is perfectly sitting onto the floor, and now let's hit play and see the result, okay. So the fluid is cutting off. So let's go into the flip object and let's enable the close boundaries, okay. So now our fluid is colliding. So to add the viscosity to these particles, let's go into the physical tab, and here we have the viscosity. So let's increase the viscosity. Let's change this to 100, and let's check, and here as you can see we have no effect. So let's go into the flip solver and let's go into the viscosity. So here onto the volume motion and into the viscosity, let's enable the viscosity, okay. And now let's see the result, okay. So here as you can see the viscosity is working. So let's increase the particles count. So let's go into the flip object and let's lower the particle separation down to 0.05 maybe, and let's check, okay. So here we have the viscous fluid. So maybe let's increase the viscosity. Let's change this to 1000 and let's see the result, okay. So now we have a very viscous fluid. Let's keep increasing the viscosity and let's hit play, okay. So now we have a very stiff fluid, okay. So let's lower down the viscosity value and let's check again, okay. And now let's animate our source. So let's go into the geometry level, and after the flip source, let's add a transform in here. Let's connect that, and here onto the transform, let's animate the translation Z. So to animate, let's use the sine function. So in here, let's type the sine, and here onto the sine, let's use the $sign F for the current frame number. Okay, and now let's see the result. Okay, so now we have a very low frequency sine wave. So let's multiply by this by 3 to increase the frequency of the sine wave, and let's check. Okay, and let's also enable the real-time playback, and let's see the result. So maybe let's increase this to 4. Let's add a 4 in the multiplier, and let's check. Okay, so the value of 4 is looking good. So now let's go into the .NET, and let's see the result with the animation. Okay, so here we are adding the viscous fluid. So you can use the viscosity to create the honey or chocolate simulation. Okay, so now let's add a noise into the velocity. Okay, to break up the fluid. So let's go back, and after the flip source, let's add a point velocity node. Let's use the point velocity, and let's connect that. And onto the initialization, let's change this to value, and let's give him a -1 value in the y-axis, and let's also add the curl noise, and let's also increase the scale. Maybe let's increase the scale to 3, and let's dive inside, and let's see the result. Okay, so now we have some breakups due to the velocities of these particles. Okay, and so let's increase the particle separation to create a more higher sim. So let's increase the particle separation to 0.01, and let's check. Okay, so when we change this to 0.01, we have a lot more particles, and simulation is too slow. So maybe let's change the particle separation. Let's change this to 0.02 and check. So let's change this to 0.02, and now let's see the result. Okay, so value of 0.02 is working good. So we have a nice speed. Okay, and we have enough detail. So if you want to add more noise detail, you can always use these particles velocities, particles forces. Okay, so in here, let's go into the point velocity. Maybe let's lower down the scale, and let's check. Okay, so now the scale is looking good. So after that, in here, let's add a pop force node. Let's add the pop force and connect this into the particle velocity, and in here let's increase the amplitude. Let's change this to 3, and let's view the results. Okay, so now we definitely have some noise. So here we have the very viscous fluid. Let's simulate this fluid for a couple of frames. Okay, and okay, so the 62 frames has been simulated. So let's see the result. So let's hit play. Okay, so here we have the viscous fluid. So that's how you can use the viscosity inside of flip fluids. Okay, now let's talk about how we can write the flip simulation to Trisk as well as how we can convert these particles into mesh. Okay, so let's go back into the geometry level. So here let's import our flip simulation. So for that we have a node called DOP import fields node. So let's add an DOP import fields node, and here onto the DOP import fields we have the preset. So let's choose the flip fluid preset. Okay, and it needs the top network. So this is the top network where we have the simulation. So let's add that, and now it needs the top node. Okay, so here we have the flip object. So this is the node where we want to import the simulation. Okay, so let's go into the top import fields node, and onto the top node let's select our flip object. Let's go into the top net, and in here let's select the flip object. Double click to select that. Okay, so here we are selecting the flip object. So let's set the display flag to the top import fields. Okay, so here we have these flip particles. Okay, and if we middle click, we have the surface, we have the velocity, and we have the particles. Okay, so in here if you don't need the velocity, you cannot import that. Okay, so if you want to add the motion blur, so you might need the velocity field to create the motion blur. So after that let's add a fluid compress node. So let's add that, and let's connect this, and here onto the fluid compress node. Here as you can see, now our particles has been changed, and now we have an epox visualization. So the particle fluid compress node will pack our particles. Okay, so in here we have the pack particles option turned on, and if we middle click, here as you can see, now we have the 12 pack geometries. Okay, so before writing the flip simulation to disk, let's add a fluid compress node to save the cache's file size. Okay, so when you have compressed that, let's add a file cache in here, and let's connect this. This one is our output. Okay, and in here you can write out the caches. So when you have written out the caches, to generate the actual mesh, we have a node called particle fluid surface node. So here we have the particle fluid surface. Okay, so this node knows how to unpack these pack particles. Okay, let's connect this into the particles and volume input. Let's set the display flag to the particle fluid surface node, and here as you can see we have a mesh, and in here we have the particle separation. So let's use the same particle separation that we have used in the .NET. So here we have the particle separation 0.02. Okay, so maybe let's go inside the .NET and let's copy this parameter and into the particle fluid surface node. Let's paste it here. Okay, so now we are referencing this. So here as you can see our mesh changes dramatically, and here we have a lot more detail into our sim. Okay, and here onto the particle fluid surface we have the option to output. So here we have the convert to surface polygon soup, so you can change this to surface polygons. Okay, or you can change this to a surface VTB. Okay, let's change this to polygon soup, and down here we have the adaptivity. So if you increase the adaptivity, okay, so let's change this to 0.01 maybe. Okay, so here as you can see we are generating more mesh where we have lot more folds. Okay, so let's add the adaptivity. Let's increase this to 0.1. Okay, and let's see this with the smooth shaded. Okay, so you can adjust the adaptivity to save the disk space as well as your memory footprints. Okay, so let's set this to default. So right click and let's change this to revert to default. Okay, so here we have a detailed mesh. Okay, so this is the mesh that we are actually going to use for rendering. Okay, so in here let's select another frame maybe, and if you want to write out the mesh, and here as you can see we have a very slow mesh generation. Okay, so after that maybe it's a good idea to add another file cache and write out the mesh cache. Okay, so here onto the particle fluid surface we have the option into the filtering, so we can enable the smoothing. Okay, and here you can increase the smoothing scale, and if we change this to smooth shaded, and here as you can see we are smoothing more detailed. Okay, so if I uncheck this, here as you can see we have these little particles. Okay, so if I enable the smoothing, so now we have a very smooth mesh. Okay, so we might need to enable the smoothing because it's a viscous fluid, so viscous fluids are smooth. So let's go into the surfacing, and here we have the droplet scale, so that's the particle scale. So if you lower this down, so let's change this to 0.1 maybe, and let's check. So it's calculating, and here as you can see we are dramatically changing our mesh by changing the droplet scale. And if we increase the droplet scale, let's change this to 2, and now we have a very thick mesh. Okay, so maybe let's change this to 1. The default value of 1 is good. Okay, and that's how you can convert your flip simulation into mesh. Okay, so now let's import this mesh into Solaris and let's render this. So after the particle fluid surface, let's add a null, and in here let's connect this and let's call this one out mesh. Okay, and up here we have the shader ball, so let's add a null here as well, and let's connect this and let's call this one out ball. Okay, and now let's go into the stage context, and in here let's add a sub import node, and from here let's select our mesh null. So here we have the out mesh, so let's select that and let's call this one mesh, and let's duplicate this sub import node, and in here let's select our out ball to import our shader ball, and let's add an merge in here. Let's merge this, and also let's rename this to ball, and after that let's add a material library. So let's connect that and let's dive inside, and in here let's create a material X standard surface material. So let's call this one mesh, and let's duplicate this material and let's call this one ball. Okay, so let's go back here onto the material library. Let's click autofill material and let's check assign to geometry, and let's drag our mesh into the slot, and let's add the ball into the ball shader slot, and let's remove this stage and from here. Okay, and after that let's add a Karma render node. Let's connect this, set the display flag to the Karma, and let's add a dome light in here, and let's add this into the merge, and onto the dome light let's select our HDRI Heaven Skylight Garage HDRI. Okay, so in here let's change the render engine to Karma, and let's see the result. Okay, so let's dive inside the material library, and here we have the shader for the mesh. So in here let's adjust the base color. Okay, so let's create a brown, and let's create a more darkish brown to create a chocolate like color. Okay, and let's go back, and here onto the dome light let's add the exposure. Okay, so let's increase the exposure a bit, and now let's dive inside the material library, and let's keep adjusting its color value. Okay, so let's create this darkish brown. Okay, and let's go into the specular, and here we can adjust the specular. Okay, so let's increase this to 1, and here we have the roughness for the specular. So right now we have a perfect shiny chocolate, so let's add a 0.1 of the specular roughness, or maybe 0.2 is good. Okay, so 0.2 is looking good, or let's increase this more. Okay, so here we can adjust the index of refraction. Okay, so let's lower the index of refraction, let's keep it default. So right click, let's change this revert to default. Okay, and now let's go back and create a ground plane. Okay, so let's change this back to Houdini GL, and let's go into the object level, and in here let's add a grid, and let's dive inside, and onto the grid let's increase the size. Let's change this to 100 by 100 to fill the entire camera region. So now let's go into the stage context, and in here let's add another sub import node, and let's merge this, and from here let's select our grid. So up here we have the grid, let's select the grid. Okay, and now let's create a material for the grid. So let's dive inside the material library, and in here let's duplicate this shader, and let's call this one ground, and for this one let's change the base color to a darkish black, and let's go into the specular, and let's increase the specular roughness. Okay, and now let's go back, and here onto the material library let's click on the autofill material to import our ground material. So in here let's rename this ground, and let's drag this null into the ground, and let's remove the stage from the path, and now let's change the render engine to Karma. Okay, and maybe let's click on this eye icon and change the color scheme to dark. Okay, or maybe let's change this to gray. So let's create a viewing camera. Okay, Let's go inside the material library and let's adjust the ground color. Let's create an even more darker ground. Okay, something like this maybe. So let's disable the light. Okay, so that's the light guide. Okay, so we actually disabled the light guide, not the light. So let's go back and let's choose the different frame for rendering. Okay, and we are not using the Karma XPU, so currently we are using the Karma CPU. So let's change this to Houdini GL and let's go into the Karma and let's change the render engine to XPU and let's render again. Okay, so Houdini have this viewport update problem. Okay, so now we are using the Karma XPU and the rendering is fast. So let's change this to Houdini GL again and maybe let's go into the animation editor and let's go into the scene view again. Okay, so now we don't have the fluid, but that's a refreshing bug of the viewport. Okay, so let's select another frame maybe. Let's go into the animation editor and let's go to the scene view, or let's change this to Karma. Here as you can see we have in the rendering. So let's change this back to Houdini GL so it's not showing up. So something is wrong with the Houdini viewport. Okay, so let's change this to Karma again, and in here you can increase the sample for create a less noisy render. Okay, so here we have the render of our chocolate. Okay, so maybe let's go into the material library and let's adjust the chocolate color and let's create a more darkish color. Okay, so let's bring the value down and also let's decrease the saturation down. Okay, so that's looks like a chocolate. Okay, so now let's go into the Karma render setting and onto the output picture. Select the location where you want to render. Okay, and after that change the frame range to a frame range that you have written out the caches. Okay, and render to disk option to render your scene. Okay, and before that we need to create a camera. Okay, so right now we don't have a camera in the scene. Okay, so that's basically how you can render your particles fluid mesh, okay, inside of Solaris using Karma. Okay, that's it guys, you made it. Thank you so much for joining in. I hope you enjoyed the course as much as I did in making it, and I hope you learned something from it, and keep up the good work, and bye bye.